Alexa? Yes. All right. Good afternoon, everyone. There's like no responses for that, so I'm going to try that again. Good afternoon, everyone. Hello. Thank you. All right. So parents and friends, welcome to UCLA. I know some of you are probably alumni, so for those of you who are, welcome back. And for those of you who are alumni, though, you probably have not been in this building in particular. So for those of you who have not been here before, welcome to the California Nanosystems Institute. So, and welcome to the presentations for Nanoscience Lab B, final presentations. Just to give you guys a quick background of where you are. So first of all, my name is Rita Blake. I am the manager of education here at the California Nanosystems Institute at UCLA. And we are a pretty unique place on campus. So most times when you hear the word department, you probably think academic department. So you think traditional things like chemistry, physics, biology, math, etc. We're actually quite different. So we're a research institute. And what we do is we specialize in bringing people together from all the different parts of STEM on campus, so physical sciences, life sciences, engineering, math, medicine, to come together and do research that is about nanoscience, which you will learn a lot about today because we have 11 presentations that will hopefully teach you quite a bit about this field. And so we do 4 sort of main things here at the CNSI. So first of all, we do team science. So we facilitate research from faculty all around the campus to do collaborative interdisciplinary research in nanoscience. We have a bunch of technology centers that house really, really cool instruments, some of which your students got to see this week, that are all about making nanomaterials and looking at nanomaterials. We've got a big focus on entrepreneurship, so we have about 20 or so startup companies that are here in our incubators, so we help foster new technologies out in the world and not just in academic papers. And then we have a big education platform where we try to teach people about nanoscience, because nanoscience is not a field that people are terribly familiar with, despite the fact that it is incredibly ubiquitous and it's one of the most exciting fields of research today, at least in my opinion. And the person I'm about to introduce has amazing timing because she just walked in the room. So your instructor of record for this course, students, as you know, was Professor Sarah Tolbert. She's a professor in the Department of Chemistry and Biochemistry, as well as a professor in the Department of Material Science here at UCLA, and she is a researcher at CNSI. She's also the faculty director of our education program. And so she got to talk with the students in the week and gave a little bit of background on her own research. And before we start with everything, she's going to come up and give some of her perspective on why we created this course, because this is a course that she created. I also have to give thanks to a couple of people, well, many people actually. If I had to list every person that we gave thanks to, our presentations would probably run over because it takes a village to run a program. But a few people I have to specifically point out, first of all, is our program coordinator, Dr. Alain Marita, who helps everything stay organized, and this program cannot function without her, and she's such a wonderful support. She's so smart, she's so creative, and she's so passionate and very sweet, and is a great person to work with. So Elaine, I see you in the back, so thank you. Yes, let's give her a hand. I agree. I also have to give a thank you to our instructors, and I don't have a photo of our instructor specifically because your students have had many instructors throughout the week, but our instructors do a lot. So these are UCLA graduate students in different labs throughout campus. Over the course of the year, they work with us a lot in providing really cool nanoscience workshops for teachers, doing all sorts of fun public outreach events. They really, really know their stuff, both in terms of the science and in terms of the teaching, and they have been incredible this week and worked so hard to make sure all of these experiments were super fun, super cool, and worked. And they oftentimes are the people that create these experiments. So instructors, and I know some of you are here, which I appreciate so much, and they'll be asking you questions. So instructors, thank you, and thank you to all the instructors here and not here. And in this course, we've got two sort of broad goals. So first, we want to expose students to more advanced topics in nanoscience, because I think most students who apply to this program have at least some idea of what nano is. They've probably read about it, heard about it in an article, or maybe they're just super curious and they research stuff on their own. But they don't have a good, tangible sense of what nano is because there's pretty much no high school curricula that actually includes nanoscience, so it's very, very hard to learn these things unless you have tangible experience with it. But we also want to help develop skills in science communication, which is exceedingly important. And we do this in a rather unorthodox way that you will see when we do the final presentations. And it's, I think, personally, a really interesting challenge, and it's much, much harder than I think even the students expected when they first heard about the program. So as you can see, they've had a very, very busy week. They learned 5 different big experiments and big concepts related to those experiments. And then in the afternoons, they got some extra exposure in these ways, either through guest lectures and then also through different activities that we went through in the afternoon. So it was a really, really packed day, every single day, and this program goes by so fast. So you will be very, very impressed, I'm very sure, at what students are able to learn and then deliver via a presentation in basically 4.5 days. And so with that, I want to turn it over to Professor Tolbert, and I'm sure she would love to give us a little bit of words on her perspective about this course and the homework and the final presentations and how cool and how important they are. So let's all welcome Professor Tolbert and thank her for being here.
Okay, is this working?
Yes.
Yes. Okay, so first of all, I want to thank all the parents for being here. You are good parents. My son is giving his final presentation somewhere else on campus, and I am not there, so I am a bad parent. You are better than me. I also want to thank all the students for spending your week with us. I know that there is a lot of really interesting things to do in the LA area and otherwise, and I'm glad that you chose this one. Okay, so I want to just give you a little bit of perspective on what you are about to see. And that is to say, what did we challenge our students to do in terms of homework assignments? And the challenge is to say that scientists in general or people in general are visual learners. And scientists spend a lot of time trying to come up with visual representations of experiments that will convey a broad meaning. So in fact, every time we write a paper that we publish in some scientific journal, we have to create a graphic that tries to capture the entire meaning of the entire experiment. And these become the graphical table of contents. And the bane of every manuscript is that you have to come up with a good table of content graphic that can convey everything about your paper in one picture. So what we challenge the students to do as their homework assignment is to create a picture that would get across the fundamental concepts of the experiment. And then we made it even harder, because when we write one for scientists, we can use any scientific concepts we want. We said, make this picture not only convey the meaning of the experiment, but make it understandable by somebody who is not a scientist. And so make your picture use everyday objects that everyone will understand, and use that as a way to convey the key concepts of this experiment. So what the students are now going to do is, so for their homeworks every day, they drew a cartoon, and then the grad student instructors gave them feedbacks on those cartoons, what kinds of things made sense or didn't. And then we picked some of the best cartoons, and we gave them to somebody else. And so what you are seeing today is groups of people explaining these science cartoons, but not their own science cartoons, somebody else's science cartoon. And the goal in their presentation is that they're supposed to explain to you the science behind the cartoon, how that cartoon captures the science, and also the limitations of that cartoon. Because anytime you make a picture that is not the real experiment, it will only capture parts of the experiment. And so to the students, I also want to ask you, please be very careful in your language. In years past, we've had lots of people who've said, here's this, and here's all these cool things, and then here's what's wrong with this picture. It's not what's wrong with the picture. It's not what's wrong with the cartoon. It is the limitations of the analogy. Any simple analogy will have limitations. It can only capture part of the experiment. And it is scientifically interesting to identify what parts it doesn't capture. That doesn't mean there's anything wrong with the picture. And so then we will also introduce the author of the picture after the presentation. And they can tell us if the group that presented really captured everything that they were trying to convey with the picture. Okay? So for students, please don't say, well, this is what's wrong. Please say, this is the limits, because that's the meaning we're trying to convey. Now, for the audience, you think you just get to sit here and enjoy, but that is not true. You have a job as well. And that job is you must ask questions of the presenters, because one of the hardest aspects of giving a scientific presentation is not presenting the part you can prepare. It's presenting the part you can't prepare, which is responses to questions. And I can tell you that as you get older and stop being a high school student and become a college student and then become a graduate student and then become a postdoctoral fellow, you never stop being afraid you're going to get a question that you simply can't answer. And in fact, you know more about this experiment than almost anybody in the audience, and you can answer them. And the only way to convince yourself of that is to just stand up here and try answering questions. And so, for the sake of your student presenters, I'm going to ask everybody to help be a part of the question process. And it is perfectly fine to ask a question simply, I had no idea what you were talking about when you said this thing. Can you explain it? Your questions do not have to be deeply insightful. They can be anything, and they still give your presenters an opportunity to dynamically respond to things that they didn't prepare. Okay, so that being said, I'm also going to apologize. I only get to be here for the first hour. I have to leave for an hour, and then I'll come back for the last half hour. So while I'm here for an hour, I will yell at all of you and make you ask questions. While I am not here for the next hour, Rita will yell at you, but probably not as loudly as I do. And so you have to get in the mood and all ask questions, and then I'll come back and yell at you some more at the end. Okay, so with that, no more chatting. Let's get on with our presentations.
So there is one small bit of chatting I have to do really quick. Okay, so first of all, laser pointer, well, not a great laser pointer, but a laser pointer nonetheless, if students, if you need it, is up here. Please. I guess, Mark, if you have a better laser pointer, we could use it. Please be careful if you're using a laser pointer. Also, for students, when you are presenting, please speak into the microphone. If the microphone is too short for you, we can't hear, and the people who are listening can't hear. So please adjust it, because again, we are live streaming. So hello to everyone watching us on the internet. And people who are watching on the internet will not be able to hear you if you do not speak into the mic. So please speak into the mic. Also, we have portable mics, so when the time comes for questions, I will be running around handing mics to whoever is going to ask them. So with that, we will go to our first drawing and our first team, which is Emma, Nora, and Becca. So let's give each group as they come up a nice round of applause.
So let me just add as they come up that these mics only pick up about 4 inches. So if you think this is talking into the mic, it's still not. It's actually got to be really close, and many people feel uncomfortable with that, but you can sort of hear the feedback when it's working. Got to just get close enough that you can hear it.
And I'll have a timer on my phone, so I'm not going to cut you off if you go over, but just so for your reference.
Okay. Hi, everyone. Thank you for being here. I'm Nora.
I'm Becca. And I'm Emma.
And today we're going to be talking about plasmonics and an experiment that we did during the week. So plasmonics is a study of plasmons, which is the excitation of electrons in response to light, and we'll elaborate more on it later in the presentation. If you guys don't know what that means, it's okay. So plasmonics has really been an important part in our lives even before we knew it. So a perfect example of this is the Lycurgus cup, which is from the Roman era and it was made by the Romans. So basically it's just a cup that if you shine light on one side of the cup and you look at it from one side, then it looks red, and if you stand on the same side as the light, it looks brown. So this has to do with absorption and scattering, which is a big part of plasmonics, and we'll also elaborate on that later too, but it's basically how the lights excite the electrons and stuff and the colors that they emit. Another example of why it's really important and it's a big part of our lives is because of the Notre Dame Cathedral, as we all know, recently burned down, but luckily one part of it, which was the rose window, didn't burn down, and that's a big part of plasmonics and how it was made. So the stained glass windows are like, well, we know they're colored, and so it has nanoparticles in them, and it's also kind of due to absorption and scattering, and again, we'll elaborate on that later. So despite the fact that the Romans didn't know anything about science and like nanoparticles and plasmonics specifically, that it was still a big part of our lives. So that's why it's also important in later times, because even though you guys might not know it, plasmonics and everything is a big part of all aspects of our lives. So now we're just going to start by looking at the analogy.
Okay, so I'm going to be talking about the top half of the picture. So the first thing you want to notice in the top half of the picture is that the citrus flower is missing for the second beaker, and this is significant for a few reasons. So I'm going to be talking about the underlying topics that we learned. We learned that you need 3 things to create stable gold nanoparticles, and this includes Au gold with a charge of 0, a reducing agent, and a capping ligand to prevent the nanoparticles from agglomerating and clumping together. And I know that that's a lot of terminology, but I'll explain. So without the capping ligand, the particles would be unstable and inefficient, and we wouldn't be able to make stable nanoparticles like we did. In the experiment we did, we used AuCl3, which is gold chloride, and citrate, which acted as both the reducing agent and the capping ligand. So the reducing agent, gold, Au has a charge of 3+, so we wanted to make that 0 in order to make stable nanoparticles. So here we see in the picture that the first beaker has citrus flower. Because it has citrus flower, the nanoparticles were not able to agglomerate and clump together, which means that we were able to make stable nanoparticles, which is why Baker 1 has a finished cake that looks good. And the second one doesn't have citrus flower, therefore they had no citrate. There was no, it could not prevent agglomeration, which is why the cake looks like a big mess. And now Becca's going to talk about the second half.
Yes. So the second half represents plasmon resonance, which is basically when a sea of electrons on a particle interact with light and they give off color. So as you can see in the first part, there's clear directions that says more milk, whip slower. So basically, the thing about plasmon resonance is that they both have to be on the same wavelength and have the same frequency to produce color. So in the picture, on the left side, the person is following the instructions, and with the lesser milk, they're stirring slower, or more milk, they're whipping slower, and with less milk, they're whipping faster. But the person on the right isn't following the instructions. So the person on the right doesn't, the product isn't right, which is the same thing with plasmon resonance, where the color wouldn't come out. But the person on the left, they're following the instructions right, which produces the color or the product. And one is still and one is thick, because depending on the wavelength and depending on the frequency, it gives off the certain color.
Okay, so next we're going to be talking about surface area to volume ratio, which we learned was really important in nanoscience. So in the experiment we did, we made both nanospheres and nanostars. A nanostar, because it has the legs of a star, has a higher surface area to volume ratio, whereas a nanosphere, because it does not have the legs of a star, has a lower surface area to volume ratio. And the important takeaway we learned from this is that nanoparticles with a higher surface area to volume ratio are less stable because it allows for more defects. The opposite is true as well. Nanoparticles with a lower surface area to volume ratio are more stable. And now Becca's going to talk about plasmon resonance.
Or absorption and scattering.
Yeah.
Yeah. So back to what Nora said about the Lycurgus cup. So as she said, you see two different colors, and that's depending on what side you see from light. So one side is absorption, and this means that the light is giving off the complementary color when it's hitting. So that's where you see the one color. And then on the other side, you see scattering, which is when the light given off returns the light, so the light's bouncing back instead of being absorbed. And that's the difference between absorption and scattering. And then that's the Lycurgus cup. So that's, as Nora said, that was the very beginning of nanoparticles. And then now in the future, we're coming up with new ideas, and that's where we have something called the photothermal effect. And this is when nanoparticles heat up due to light being shined on them. And this is used to target tumor cells in the body by, the nanoparticles are directly targeted at the tumor cells, and then this activates the first line of defense in the immune system, which is a lot less invasive than chemotherapy and risky than chemotherapy. So we're developing new things. So even from the Lycurgus cup, which was so long ago, and then also now photothermal effect, which is we're developing right now, nanoparticles and plasmonics is being used throughout time.
Okay, so the last final thing we learned, or the biggest takeaway from this experiment, was that plasmon resonance and the colors they emit depends on size and shape. Size and shape is really important. Changing either the size or the shape or both can create new localized plasmon resonances that would change the colors absorbed and thus the colors reflected. And so these are the 5 main topics that we learned on plasmon resonance. Thank you.
Okay, questions?
No.
All right.
Hi there. Great job, guys.
Thanks.
Very interesting. So you referred to some back in history nanoscience, both the color in the glass for the rose window and the Lycurgus cup. And you mentioned that that was a first use of nano. What are the nanoparticles or nanostructures that go into that glass? Were they doing something special without noticing it, or is it inherent in every object?
Basically, they were doing something without noticing it, because what gives off, like in the stained glass window, it's gold or silver nanoparticles, which is in it, but this gives off a different color. So technically, they're using the metal, and the color comes off, but they didn't know that was the connection to it.
Yeah, so they must have been doing something without realizing what they were doing,
Yeah.
because obviously they didn't have the knowledge that we have today about nanoscience. But throughout during the process of making the glass structures, they were able to like create nanoparticles, which is why we have that like rose color effect that we see in the rose window in Notre Dame.
Other questions? So just one comment. Okay, just one comment for you guys. Yeah, what they did is they just dumped gold or silver into their vat of melting glass and said, "Oh, the color changed." They didn't say, "Oh, I'm making gold nanoparticles,"
Yeah.
but actually they were making gold nanoparticles. The gold they dumped in there aggregated into little nanoparticles. So that's exactly the question. Oh, you have your own mic.
Okay, so my question is about the top half. So you mentioned that the citrate has two purposes, right? So which purpose do you think it's serving here? You said?
Oh, okay. So in our experiment, citrate acted as both the capping ligand and the reducing agent. But thank you for pointing that out, because we wanted to talk about, so the artist of this drawing included milk and citrus flower. And here, citrus flower acts as the capping ligand, because milk we see is negative, or she talks about, if you can see the label, I'm
It
not sure if
says
you can.
underneath, it says, our milk is so cold it's negative, which also reacts with the gold that we use, because gold is a positive charge, and since the milk is a negative charge, would reduce the gold to a neutral charge.
Yeah.
AU0, which is what we needed to make those stable gold nanoparticles.
It could be the capping agent. It could also, I think, be the reducing agent based off of the results, I would think. Maybe. Right? Because in one case, you have something that does look like it's one agglomerated piece, right? The cake. And then in the other case, it sort of looks like a disjointed mess. So it could be, I think, possibly the reducing agent. But you mentioned that the citrate does both of those functions.
Yes.
Yeah.
So it could be either. I guess we'll
Yeah.
find out when we ask the artist.
So then my question is, what are the limitations of this? Well, I didn't want to tell people not to talk about that. I just want you to use good language when you do so. This captures some aspects of this experiment, but surely baking a cake does not directly or completely map onto making gold nanoparticles. So what are aspects of the experiment that are not captured in this?
Well, I think the shape and size she couldn't really incorporate into the thing, because it would be hard to kind of incorporate it into this analogy, but shape and size also do play a really important factor.
I do actually think that the shape is a part of it. If you look at the two whipped creams,
Oh, yeah.
I think
Yeah,
they
I
do.
guess so.
So how would those track? So which one is representing which, do you think?
For shape and size?
Or at least for shape.
Wait, sorry, could you repeat the question?
Yeah.
So if you look at for the successful baker, they've got two different whipped creams, right?
Yeah.
They look like they're different shapes. So how does that relate then to the different shapes of the gold?
Oh, so like we talked about in the presentation, we learned that size and shape have a effect on like the kind of like color that is emitted, which is why we see that like when she uses like the different sizes or shapes of the whipped cream, they created different products, which was one of the points that we learned in the experiment.
I think just to quickly clarify, I think one of them has star-like peaks to it, like spiky. It's like a spiked, stiff peaks, and the other one's got like more globular, spherical shapes. So I think that was another intention of the artist as well.
I think my eyes are too old to see the difference
Yeah.
between the stars and the globes. Okay, one more question. Oh, audience.
Oh,
Yes,
okay.
awesome.
So you mentioned briefly the medical aspect, like with cancer.
Yes.
And I know that the rest of the presentation, I may just have missed something, because you know a lot more than I do about this. Talked about gold and almost about a visual image. how is this part of the medical part? Is it the light that it shines in a certain item? Is it how you can read it? Or did you just mean that's nanoscience in general?
Well, it relates. So in our experiment, we were making nanoparticles, and so those nanoparticles will be implemented into the body systems, and that's how it relates to biomedical. So like the things we were making in labs and stuff, they have the ability to the photothermal effect. We didn't explore that area in our experiment, but that is another aspect that nanoparticles have.
Okay, but let me just ask a clarifying thing. So you talked about the fact that you made different kinds of nanoparticles and that they could absorb different colors of light based on their size or their shape. And that's the essence of this experiment. What is the photothermal effect? So after you absorb the light in the photothermal effect, what do you do with that light energy?
Well,
I don't know if we can answer that question very well, but like we'll try. So
Yeah.
what we learned about the photothermal effect is that when nanoparticles have light shined on them, they're like open to like a wider range of capabilities and like applications.
Yes.
So one of the applications like we
Is
talked about
heating.
is the being able to specifically target tumor cells in the body.
But would just go back to like the name, photothermal.
Photothermal.
I think it's taking the light
So it's
and
taking
it's
the light
releasing
energy,
heat,
yeah,
and
and
so
turning it-
as it releases heat, then it kind of kills the cell.
Yeah, that's all it is.
Oh, okay.
It just absorbs light, and metal nanoparticles really efficiently turn that light energy into heat energy.
Yeah.
So they can locally cook things wherever they are when they absorb light. That's
Yeah.
all there is to it. This is our whole point. This nanoscience is not big voodoo. It's simple, but it's cool.
Yeah.
It's always simple. Okay, that was an awesome presentation. Thank you guys very much.
Thank you.
Also, can we get the author of this or the artist behind this drawing to stand up and talk about their drawing? So did they, is there any additional concepts that you were going for that weren't discussed?
Well, I think they captured like what I was trying to go for pretty well. But actually, you made an interesting comment about like the circle and star whipped creams, and actually that's unintentional. I didn't mean to do that. I just meant to depict the different textures, because actually what I was going for was that the different like sizes of the milks turn into different like textures, which is supposed to represent the different like colors of light. So that's what that was. Wow. But otherwise, I think they really got into like all the details I was trying to portray. So.
All right. All right, so next group, Ryan, Nathan, Haig, come on up.
We're good? All right. Wait, can I hold it? Yeah. All right, cool. Are we good?
Yeah.
We're good, okay.
Good afternoon, everyone. My name is Haig,
I'm Ryan.
And I'm Nate.
and today we will be explaining a fundamental concept that we learned throughout this week. So, as many of you know, founding father Benjamin Franklin was very well known in his efforts for the American Revolution and his efforts in drafting the Constitution. However, he was not commonly known as a scientist. Benjamin Franklin has done many experiments throughout his career. However, one that really stands out was one where he was trying to impress partygoers. In that experiment, Benjamin Franklin took a cane, and on the bottom of the cane, he put a drop of pure oil / oleic acid, and took that cane to a lake and put the bottom of the stick in the lake, which then eventually calmed the lake water. And many people throughout history have tried to understand this phenomena, but never really got it. So today, we are here to explain the why to this phenomena.
Yeah, so as Haik said, yeah, we're here to explain the why of this phenomenon that people in the past have always seen that oil calms water, oil makes water more stable, but they never really understood why this was. So this is our graphic illustration. And I've always thought that illustrations are really good to like depict scientific things. So here's what we're going for. We're going for, there's two concepts really that's in this illustration. It's the concept of the amphiphilic molecule, which is the cat and the fish, and the concept of indirect measurement, because at the nanoscale, we can't exactly take a super tiny ruler and measure these things because obviously they're tiny. And so the only way we can really measure these things is to measure something that is actually measurable, such as the diameter of something, of like an oil spill, and then we have to extrapolate based on data that we have received. So amphiphilic, we all know amphibian, land and water. We know we're an amphitheater, right? There's two sides. So amphiphilic refers to the point where there's two ends of this molecule. The first end, as we can see with the cat, cats don't like water, so it's hydrophobic end. And we see the tail, which is of a fish, and fish love water, so it's a lipophobic end. And these molecules that we saw of oleic acid are, they arrange themselves in an order so that they form a one molecule thick layer called a monolayer. And in this case of oleic acid, it's 1.97 nanometers. And what we found was that they naturally stack on, if you put it on water, as Benjamin Franklin did in the lake, it would calm the lake by forming this very small, thin layer on top of the water, calming it. So that's the cat allegory of this part of the representation. The second part that we see is the indirect measurement. We see a man he's slightly much smaller, and he's holding what we call a surveyor's wheel to measure the length between him and the particle, and he's also holding a protractor to measure the angle. We also did some math, and that's this is one of the limitations where you can't exactly demonstrate the exact form, the exact math that we did, but this is a very good example of indirect measurement, how we can take an angle, take a side, and we can find the height of something by using trigonometry and SOHCAHTOA. So those are really the two aspects that really is covered in this illustration.
So I'm going to go into more in depth about what we actually did in this experiment to find the length of one oleic acid molecule. So what we calculated first is we found the volume of the oil we're going to drop on the water, and then we measured the diameter of the oil when it spread across the tub of water. And because it's a monolayer, we know it's like a cylinder where the radius is the oil spill, but the thickness is only one molecule thick. So if you know the volume that you dropped into the water, and you know the radius of the circle, you can find the height, which ended up being 1.97 nanometers. And the interesting thing about this number is how small it is in comparison to everything else. So it would be impossible to view this with the naked eye or even with a light microscope, as the smallest wavelength of light is about 400 times larger than the molecule itself, so it would be actually impossible. But you can do it with advanced electron microscopes, but not many people have these. So it's really interesting how you can calculate something so small using standard math and critical thinking. To give you some scale about how small this actually is, 1.97 nanometers is to a soccer ball as a soccer ball is to the entire planet Earth. So this number is so insignificantly small. However, we're able to determine it using nothing but our heads, which is really interesting. And this is the fundamental principle of nanoscience, where a lot of the times we can't actually measure what we're looking at. Thank you.
So yeah, questions?
So I was wondering, why is it that one end of the particle is attracted to the water, but the other end isn't?
Right.
All right. So if we delve into the physics, or not really, the chemistry of how the molecules, one end is polar and one end is nonpolar. And if you see in the substance that is, it's water, right? Water is polar, and polar things like other polar things, while nonpolar things like nonpolar things. It's kind of like a magnet. So if you arrange these items jumbled together and just put them into this medium where it is separated, the nonpolar side would like the nonpolar side, and the polar side would like the polar side. Therefore, what we see is that the molecule will orientate itself so that the polar side would be in the water, and it will be one cell thick.
Okay, but let me just add to that. Can you define polar?
Yes. So polar, it's a chemistry topic where electrons aren't distributed evenly across a molecule. So certain atoms, like oxygen, are very grabby. They like to pull the electrons very close to themselves. This makes the atom slightly negative because electrons are negatively charged. And that means the other side of the molecule is positive. So it's a very slight differentiation in charge. And this is why water forms hydrogen bonds. And it's actually really important for how water works and how chemistry works in the real life. So on an oleic acid molecule, it has an oxygen and hydrogen group at the end, which makes it polar, and the rest of it's just carbon and hydrogen, which does not share electrons unevenly, which makes it have no charge and thus nonpolar.
That was an awesome description. You could come teach freshman chemistry here. Okay, other questions?
How much margin of error do you think you have in your measurements? Because dealing things on this scale, even if you're off by a little bit in your volume or in the radius, it could mean the thickness of the molecule could be off by quite a bit.
Yeah. So what we found in our experiment was that sometimes we would get the value of 1.97, but we wouldn't get that value. We would get that value multiplied by maybe 4, so we get 8, or maybe by 5 we get 10. So then we could see that, we didn't mix the oil and the water because we diluted the oil well enough so that when we put it onto this medium, which is water, it actually formed not a monolayer, but a layer of 5 molecules instead of what we intended for, which is 1. And again, also, if you don't mix properly, you won't get a circle, but rather you'll get an irregular shape. So that will also maybe screw up your calculations.
There's a very fine, it's a very fine measurement, and we got quite a bit of error, but we did multiple trials, but we got relatively close. We were within I think 10 nanometers, which it is very small, but considering we were measuring using rulers and graduated cylinders that weren't even perfectly accurate, it was really surprising how close we got.
But I actually think you guys said the right answer, which is way bigger error than whether you exactly measured it right, was whether you have a monolayer or a bilayer or a trilayer, because there are other ways to arrange. But, order of magnitude is actually good at this length scale. So within the right factor of 10, you're doing awesome. Okay, is there one more question? Well, I have a question. If you. Okay, so I will ask my always question, which is, so what are the limits? So I have actually 2 questions. My first question, which you can answer as my real question, is, so what are the limitations of this experiment? It describes many aspects of what you did, but not all aspects of it. And then my second question is, why does a monolayer of oleic acid on a surface of lake calm the waters of the lake? Okay. Not that you necessarily need to know lake hydrodynamics, but I would like to know what Benjamin Franklin was actually doing.
All right, so I can tackle the first one. So
Yeah.
there's
The second one you don't actually have to answer because
right.
I don't think we know the answer to that.
So there's a couple limitations that I think that I see, especially because this is not the way that we actually calculate the thickness of this molecule. We did not calculate it in a triangle and use trigonometry. We actually used, as Ryan said, we calculated it as a cylinder, as just a really thin cylinder. And the other thing is that we only see one molecule rather than multiple molecules arranged together in one monolayer. So yeah, I think those are two limitations that I see.
That's good. Any guesses on why a monolayer of molecules would calm a lake?
Is it because like the hydrocarbon tails, they're attracted to each other, and it's stronger than like all the water that's shifting around, and it smooths it out?
I don't know the answer. I mean, the hydrocarbon tails do interact, and there is some cohesive interaction, but it should be an energy that is so astronomically low compared to the energy of a wave that I can't quite see why it would do any good. But I'm going to take olive oil next time I go to a lake and see what I can do. Okay, thank you guys.
Thank you.
And then can we get the artist to stand up for this one? Anything you wanted to add to their explanation?
No, I think everything was generally covered. The main thing I wanted to show within this drawing is the fact that when you need indirect measurement, it's generally because you can't directly measure something.
Great. Okay. Next team, Janine, Aimee, William.
Sure.
That's in order.
Okay. Well, okay. So you're probably wondering who we are, and so hopefully future nanoscientists. But in terms of names, I'm Aimee.
I'm Janine.
I'm William.
And so on Wednesday, we studied how silver nanoparticles affect yeast cells and biotoxicity. And so biotoxicity is pretty self-explanatory. It's basically studying things that are toxic to various organisms. And silver actually has a very special ability to kill single-celled organisms, and it's in a lot more things than you think. But it's been present and used in the same way as antimicrobial throughout, forever. So basically, I think it was the Romans, but a lot of people throughout history have put silver spoons in the bottom of milk to keep it from spoiling, or place spoons with their meat to keep it fresh. And so it's basically just it kills the bacteria, and we'll get into more of how that works later. But it's also in teddy bears, which you might not expect. Manufacturers realize that, oh, this thing kills germs, so at least most germs. So let's put in the teddy bears so your kids won't get sick. So it's in a lot of things just to keep things cleaner and just generally safer. And on another note, it's actually used in beauty products sometimes, and it's in other antimicrobial creams. So there's a lot more specifics to this, so Janine will get into that. Okay. This week, as basically everyone has said, we had to draw pictures for homework. And so this lovely picture right here is definitely check plus quality. And so Wednesday, we learned about biotoxicity of nanoparticles, and as Aimee mentioned, so during our lab section, we tested different types of silver and how they damaged single-celled organisms, which in our case was yeast. So we tested silver powder, silver nanoparticles, and silver ions. And this analogy represents the results based on our different types and methods of entry into the yeast. So the theater on the top, far left, depicts the nanoparticles. Nanoparticles are transported through endocytosis, which is basically when a cell engulfs particles like food in a sort of capsule, like a bubble, and then it brings it into the cell. And so this is represented by the person in front on top hiding the other people within the large coat. And then, yeah, the one with the top hat hiding the other people. And so then the person enters through the door, and then the nanoparticles will be released into the theater, which is the yeast cell. And so in the middle, on the top, those represent the ions, which move into the cell by ion channels. The ion channels usually transport small positive ions like sodium or potassium. And so this analogy shows this by the people going in through the front door. And an important feature to note of this drawing is that this is a different door than the one the nanoparticles used. And that's because they have different methods of entry, endocytosis versus ion channels. And so on the far right, this represents the silver powder. And so ions have to break off the larger silver particles in order to enter the cell. The silver particles are actually larger than the cell, I believe. And so in order for it to affect the cell, ions have to break off of it. And so this analogy shows this by the people going in, through like the clump of people at the bottom, which is like the powder. And then one by one, they're like breaking off and going in through the door. And the method of entry is the same, the ion channel, because the ions are breaking off. So now, if we look at the bottom half, this shows the extent of the damage each type does, which we found out during the lab. And so the left side, nanoparticles do the most damage to the cell, which happens in real life because they are the smallest and fastest particles to enter. And so ions do the second most damage because they, nanoparticles also have the ions that break off, but that happens like inside the cell. And so that happens faster because nanoparticles are a lot like smaller. They have a higher surface area to volume ratio, which makes them unstable. And so ions do the second most damage because they're slower than nanoparticles. They have to go through the ion channel. And then the one that does the least damage is the powder because it doesn't directly enter the cell. Ions have to break off of it and then enter the cell, so it's very slow. And so William will explain a little more about the experiment and then other key biotoxicity concepts.
Yeah, so a little more things to know in addition to this analogy. So first of all, we also tried the same experiment but with gold nanoparticles, and we found out that the gold nanoparticles actually don't do any damage to the yeast cells because the gold nanoparticles can't attack the yeast cells due to their they can't get oxidated as quickly as the silver nanoparticles. And I'll also explain how the silver nanoparticles penetrate the cell. So first, the silver nanoparticles enter, their ions enter through ion channels, and then the ions react with the oxygen inside the cell, and then the nanoparticles form reactive oxygen species that prevent the yeast cells from performing cellular respiration and also break down the cell membrane. And so the yeast cell dies due to both protein dysfunction and the breakdown of its cell membrane caused by its inability to perform cellular respiration. And I also wanted to explain the manometer, which we use to measure the amount of respiration the yeast cells had. So basically, you have like a U-shaped container, and we basically fill it with liquid, and on one end of it, we put the yeast container, and then we completely seal it with parafilm, and then we can measure the yeast cells' respiration by looking at the water level change on the left of the U. So that's how the manometer works. And do you two have anything to add to that?
Thank you for listening, everyone.
All right, thank you.
I think we're done.
That's like the most important thing you can say in a talk is the thank you for listening, because otherwise the audience is paralyzed with fear, not knowing whether it's time to clap or not. So you have to save the audience, and you have to eventually say, thank you, you're allowed to clap now. Okay, questions?
So this is a non-expert question. What are the practical uses of each of the different forms of silver, if you know?
Well, they are able to kill single-celled organisms, and in this experiment, we used yeast. So once we introduced the yeast, it was able to kill the organism. And so basically, if you add a layer of silver particles, silver nanoparticles, it's able to kill the single-celled, the microbes and the single-celled organisms there. So it basically it cleans it sort of, but just in a different way.
So I know that you mentioned some things, but other than teddy bears, do you want to mention some practical products that have silver in them?
Yeah, there's the microbial cream that I mentioned, and it's you can get it at CVS, and basically it's used to help dress wounds and clean it so it doesn't get infected.
There's Band-Aids.
Yeah.
There's gym socks. Okay. Other questions? Okay. While you're going, I'm going to ask a question as I walk. So yeast is an example of what kind of organism? What are the other things you might bump into that is in the same family as a yeast?
Prokaryotes?
Well, I mean, so there's bacteria. You say microbes. Yeast is not a bacteria.
Right.
It's an example of another sort of big class.
Fungi?
Yeah, fungi, yeah. And that's sort of the stuff that often, well, both the fungus and the bacteria stink, but they're both part of the things that make gym clothes stink. Okay, I was coming over here for somebody's question, but I remember who.
So given the human body is also made up of cells, is using silver going to kill me eventually?
So no, because we have a lot of cells. But actually, an interesting thing is that those creams that Aimee mentioned are not approved for use on pregnant women because the silver nanoparticles could actually kill the embryo because that has so little cells. So the silver nanoparticles won't be damaging to an adult or in the long run because we have a lot of cells.
Did you get told about the blue person?
Oh yeah.
Oh,
okay.
right.
So there was actually a man who consumed too much silver, and I don't really remember how he did that, but he drank the silver.
I'm not positive.
Yeah, and so he actually turned blue. Yeah.
But he was fine. So oddly, it's apparently really not toxic to humans. Okay, one more question. Going once? Okay.
So I was wondering if you could, sorry, not close enough. I was wondering if you could explain a little more the difference between the middle picture and the picture that is audience right. It seemed like in both cases you were talking about ions going in. It's just that the third one, that was the silver powder, and so they were coming out of the clump. And it wasn't clear to me why the version coming out of the powder with the clump would cause less damage, which seems to be what the picture is showing here.
Right. Ultimately, the ions are what's causing the damage, but in the far right picture, they're coming off at a lot slower rate because they have to break off and then enter the ion channel, whereas the ions just have to enter the ion channel from the solution. So just because of the slower rate that they enter, that's why they cause less damage.
Yeah, there's just way less of them in the end. Okay, so I will ask you, what are the limitations of this analogy?
So it didn't really depict, I guess, how the actual experiment was performed, with the manometer and measuring the cellular respiration, like it does show like how the damage differs between the different types, but it doesn't show like how we measured that, which is how we actually did that in the experiment.
Any other limitations?
It doesn't show, I guess, the mechanism by which it causes the damage, like within the highly reactive like oxygen species.
Yeah.
Like
Yeah.
within
It
the
also
cell.
doesn't really show the mechanism for going in, just different doors. So it's not trying to portray that part of it. Okay, excellent job, guys.
Now it's on. Okay. And then the artist.
What they ended up saying was pretty dead on for what I went for. I don't think they missed anything. But I think part of what her question was of like how the silver powder didn't do as much damage is maybe a little bit of an issue in my drawing of I have about the same amount of stick people entering in the middle as I do on the right. And so that might be a little bit of an error on my side of maybe there's just some less people going in. And so that's part of why it doesn't work as effectively.
Or not an error, just, yeah, a limitation maybe of the analogy. But it's still pretty good. And very funny. Okay, next group. So Milo, Ari, and Heijun.
All right, hi guys. My name is Milo. This is Hyejun, and that is Ari. And if you guys were ever wondering about like how maybe your phones, laptops, or like modern day electronics work, even though they're so small, you know, like how they work so fast, how they can store so much information, we're hoping to kind of like let you understand a little bit more. So what lets this all happen is photolithography, and that is the process by which you microfabricate a pattern on a thin film or a bulk of a substrate. And because you have to be really precise when you're going for really tiny circuits, so you have to go to like the nanometer range. And with photolithography, that's possible. And that's our image we're going for, I guess.
Yeah.
it's on to you.
So I guess it's my turn. Obviously we didn't make the Intel sized computer chip photolithography circuits, but we did a much bigger version in the lab, and so this is the analogy sort of that shows it. The first sort of base layer of when you're doing photolithography is a substrate, which you can just think of like a just anything that everything goes on top of, kind of like a base. And then on top of that, you put whatever metal you want to be doing putting a pattern on, which in this analogy is the grass. And then really the first step in photolithography is to put this layer on top of the metal, which we like to call a photoresist. And really that's just kind of this material that when light hits it becomes soluble in water, or actually not water, what's called the developer solution. And so that photoresist is represented by the snow here, and what's being coated by the snowing clouds. The next step is masking. And so they kind of did two steps in one here, but these clouds here are preventing the light from reaching these two these two patches of snow, and that kind of leads me to exposure, which is when we shine light on the wafer, and the parts that aren't covered by this mask, or in this case the clouds, get exposed and are washed away by the developer solution. But in here, because it's snow, it just kind of melts away. And then the next step in the process is etching. So this is sort of represented by these lawnmower corporation little guys. But basically, the etch solution gets rid of all the metal where it's not covered by the photoresist. And so in this case, the lawnmowers obviously can't mow over these huge patches of snow, so everything else goes away. And then in the end, you're left with no grass in the areas. And then obviously, they didn't show it here, But the final step would be to remove this snow, and you'd have little patches of grass here and here. And there's one, that's sort of the process. And there's one other big idea that this analogy is trying to show. I don't know if you guys can see it clearly from your point, but there's this dialogue that says no more gas. And again, here you can see this little patch because he didn't have enough gas. That sort of speaks to like a theme in photolithography. As you get smaller and smaller and smaller, and you're trying to make smaller things and everything gets closer together, the holes in your mask, so that would be the distance between between this cloud and this cloud. Sorry, the laser pointer is getting a little small. Becomes so small that they start to mess with the light, and you're not able to accurately expose. And so what we need to do is, you don't normally think of light as having sort of like a size, but in the nano world, everything is so small it really does matter. And so by the higher energy light has, actually the smaller it is, it has a smaller wavelength. And so the more gas sort of correlates to we need more power to make a beam of light with more power. And so you can get small enough to really be accurate and really get everything you want to get. And so that's why that grass, that little patch is there. And if they had more power, they would have been able to get rid of that.
So actually the illustration showed positive photoresist. And so a limitation was that they didn't show negative photoresist, which is when the light strengthens the metal instead of weakening it. And as feature size decreases, it becomes harder to control resolution. And so Gordon Moore is the creator of Intel as well as an engineer. And he created this prediction that known as Moore's Law that predicts every 2 years the size of transistor halves, and in turn, they double in efficiency and speed. Which means, but they also get increased resistance in the transistors. So it is important to find a material with low resistivity, which is how easy it is for electrons to pass through a material, whereas resistance also takes into account size and shape of a material. So a high resistance can lead to energy lost as heat. And so one of the things we need to make like a photolithography, like to do photolithography effectively, is a clean room for semiconductor manufacturing and photolithography, because we don't want other light waves and dust to interfere with our experiment, because usually photolithography is like done at a very small scale, so even dust could like really ruin your experiment. So that's why we did a larger scale photolithography experiment instead. And so thank you.
Yeah, any questions?
What was the metal you used?
All right, so we actually used copper, right?
Yeah.
And then at the bottom of it was substrate.
So often in clean rooms, they have kind of orangish, reddish light. Can you explain why they would use that versus, white light that we have in our rooms regularly?
Sure. So once the photoresist layer is coated, is put on, you want to have no light exposure, because that's going to start to eat away at that photoresist. And you don't want to have any exposure until you have your mask on and everything's really set up. And when we went to the clean room, they were telling us that orange light is much less destructive to that photoresist, because it's on, because again, orange light is on a longer wavelength, and so it basically has less energy, and so it's like less destructive to that photoresist.
Can I leave this mic with you, Andrew, so that I don't run around? Other questions? All right, so I have a question. So you mentioned positive and negative photoresist. Can you elaborate on how those actually function differently? Like what makes a resist positive versus negative?
So positive is you use the light to strengthen the metal, and for negative photoresist is you use the light to strengthen the metal, so that like the metal that wasn't covered with light is the one that you chip away. But positive photoresist is when the light actually weakens the metal instead. So that is the part that you lose.
Strengthens or weakens the metal?
Or the photoresist?
The photoresist,
Yeah.
right? So how would it, in the negative photoresist version, how would the light strengthen it? What is it actually doing to the resist? Do you know?
I'm not too sure.
Basically, the photoresist in that case is made up of a lot of single sort of strands of plasters. I think it's like that. And when you apply light, it sort of bonds them into this polymer, which is much harder to wash away.
And then in the positive photoresist, what is it doing then? By contrast?
I believe in the positive photoresist, it's weakening the molecule somehow to allow it to be washed away. I'm not 100% sure about that.
Yeah,
Sorry.
it's just breaking bonds, right?
Mhm.
So in a negative photoresist, you're cross-linking the polymer, so you're taking all these different strands of resist and linking them together to make them even stronger, so that they're insoluble. And then in the positive photoresist, you're breaking, by contrast, you're breaking the developer, the photoresist down, so that when the developer comes in, it's soluble and it can take it away.
When might you use negative or positive, the negative or positive method? What's the use case?
It really depends on like what you're trying to do. Different applications. Photolithography is used for like a lot of different purposes, and there's so many different applications. But it would have to be like on a case-to-case basis. Just different ways of doing things.
All right, thank you. Good job. Okay, one quick question.
With lithography, they use 4 different color negatives. Cyan, black, same like you see in your laser printer at home, color printer at home. Would the number of filters, if you will, affect the number of negative, positive, all that? Will it have an impact on it? I'm not sure.
I'm sorry.
Well, lithography uses 4 primary negatives when you're doing lithography.
Oh, like on your printer at home with the.
Well, the printer's in the modern version.
Okay.
The original version was actual film with negatives. You have 4 separate negatives that you would use to filter the light through.
So sorry, I think I get what you're saying. Lithography is just sort of like a blanket term that we use to describe when you have sort of like one mold, like almost like a stamp as a form of lithography, and you can stamp that a bunch of times. And so there's different ways you do lithography for different things. For instance, this way for nanoparticles, a stamp, or in printing, it's a little bit different, but it's still this whole same general concept.
Okay, thank you guys. And then would the artist for this one also please stand up? Did you have any extra things you wanted to add to their explanation of your drawing?
No, I think they missed one part, which was I actually meant for the lawnmowers to like depict resistivity too, because the length of one of the lawns was like longer than the other. I don't know if you could see from here, but the 2 lawnmowers on the right work for a different company than the lawnmower on the left. So they actually have to use more energy to mow their lawn because obviously their lawn is bigger. So I just tried to depict resistivity there because the longer your tube is, the more energy it dissipates and the more energy you have to use.
Cool. All right, thank you. Okay. Next team. So while this team is coming up, I'll actually explain sort of an interesting case scenario for 2 of our teams. So 2 of our teams did their experiment today, which is the one that you're about to hear about. And they actually had a more sort of different and specific challenge because they obviously could not do their homework in the evening. So they had to do their drawings right after the experiment. So this group had, I guess, less than an hour basically to figure out their drawing, and they're going to present on the other team's drawing because we had 2 teams do this experiment and 2 teams, everyone did this experiment, but we had 2 of the teams who did do the experiment do drawings and then trade drawings. So this team is going to be presenting on the other supercapacitor team's drawings, and they're going to tell you what that is right now.
Okay, hello everyone. My name's Katarina.
I'm Ellie.
And I'm Anna.
And today we're going to be talking to you about supercapacitors and the role that nanomaterials play in them, which, again, we just learned this morning. So in today's role, conserving energy and finding effective forms to preserve energy is really important and crucial in order to resolve our environmental problems. And so one way to do this that is currently still under research is if we can develop ways to find batteries that can store enough energy and charge faster. So if you could imagine your phones or your electric vehicles charging in a matter of seconds or even minutes and still using that energy that you put into your car or phone and use it for very long periods of time, that's exactly what supercapacitors can help us be able to do. And so there are two ways that we store energy, and that's through batteries and capacitors. And so what we learned this morning was how batteries have a high energy density, but a low power density. So if you can imagine, an analogy for this would be like a young child who has a lot of energy, but they don't have a lot of power. That would be an analogy for how batteries and their energy densities work. But a capacitor has a high power density and a low energy density, kind of how a power lifter lifts very heavy dumbbells, and they only usually do it once, but they use all of their energy and all of their power in that one use. But supercapacitors have a perfect balance, and they are a perfect bridge of what batteries do and what capacitors do. So they have a high power density and a high energy density. So what makes supercapacitors very effective is the use of nanomaterials. So what we did this morning when we made our own supercapacitors was we used a nanoporous material, which was carbon. And why they're so effective is nanoporous materials and nanomaterials in general have a very high surface area, which means that because of the high surface area, they have the ability to withhold lots of energy, which is why they're a very good use for batteries and withholding all of this energy. So this combination of fast charging and longer lasting batteries results in lots of energy saved and could definitely resolve some environmental problems.
Okay, so I'll be explaining the analogy. So we have 3 runners here, all in an 800-meter race. And so all of the runners each represent a different storage device. So starting off with the first runner, they are a mile world champion, so they are used to running a longer distance. And as you can see here, they have a great amount of energy and are able to finish the race, however, at a slower rate than the other racer. And this is because this symbolizes the battery. And this is because the battery has a high energy level and is able to do things over a greater amount of time, however, it has less power. Then at the bottom you see a sprinter who's used to running 100-meter races. As you can see, they start off strong, but they fall flat and don't even finish the race. And this sprinter represents a capacitor. And it has a high power but very, very low energy, so it is unable to finish. And then in the middle we have an 800-meter world champion. So they're used to running this race, and so they have a high power and a higher energy level. However, if they were put in a 1-mile race, they wouldn't be able to finish as fast as the battery. Therefore, it represents a supercapacitor, so it's an in-between of both the battery and the capacitor, so it has higher power and higher energy.
So there are some limits to this analogy. So it captures why supercapacitors are better and how they differ from batteries and from normal capacitors, but they don't show some of the science behind why that works. And so at a nanoscale, as previously discussed, carbon, we used activated carbon, which is a nanoporous material, meaning it has very small holes in it. And this means that the small particle has lots of surface area. And this combination of a high surface area and this ion that is connected to another panel means that there is also a short distance that it has to travel. So this combination between the two means that these supercapacitors create an efficient balance between power and energy, as depicted in this analogy. But the usage of nanomaterials to create fast charging storage devices that we can use over and over allows us to more effectively store and use energy.
Thank you. Thank you.
Questions?
So, if these supercapacitors are so effective and they charge fast and they store a lot of energy, then why aren't we using them everywhere? What are the limitations that stop them from having taken over the world?
They store a good amount of energy, but not for long distances of time. So like they have like buses in like China or Japan, and they run on supercapacitors. However, every time they stop, they charge because they are unable to hold that amount of energy otherwise.
And just to add on to that, an example is in Tesla cars, they do have supercapacitors, but they also have batteries. So an interesting thing about specific to Teslas is they use supercapacitors for high energy bursts. So going from a quick range of speed from like 0 to like 100 miles per hour. They use that for the very quick power jolts, but they also use the batteries to keep the supercapacitors running. So they still use the batteries to kind of support the supercapacitors, and that's still kind of, as a science community, we're working to just make the supercapacitors more effective.
So I'll add on to the question. So I think you mentioned a couple of applications. Can you give a few more, like especially for capacitors?
Well, for us in our experiment today, we actually used it to charge light bulbs, where you saw that something that's battery powered, where in our instance it was actually plugged into the wall. We saw that it was more effective in the battery sense, but in the supercapacitor sense, it could you could charge it way faster than you could with a battery. You turned it on for 30 seconds, and then you could run it for 30 seconds. So it was charging super quickly. And so I don't know if I have a real-life application, but that's what we used to do.
That is actually interesting that you mentioned that, because there is one application where you want a flash of light, and they actually use capacitors for it pretty frequently.
Mm-hmm.
Can you think of what that would be? If it's a flash of light?
Sirens, a flash of
strobe lights.
So what instance would I want to use a flash of light for something? Like if I wanted to, say, capture something. For a photograph, right? So actually a lot of cameras, especially like digital cameras, utilize capacitors to recharge and discharge quickly the flash of light, because for those big, nice flashes, I mean, not probably for your cell phone cameras so much, but for like digital cameras and the ones that they use in the studio, they actually use capacitors for that pretty frequently, because you don't need a ton of energy, but you need energy very quickly. So that makes capacitors a really good case for that. So it's kind of like you guys were saying, there's no like perfect, like supercapacitors don't need to be used for everything, but they're very, very good for some things, just like batteries are good for some things and capacitors are good for some things.
Hi. What kind of effect does heat have on the storage of energy? And the reason I ask is a lot of times people will keep their batteries in a refrigerator, or on the Tesla car, if the car gets hot, it reduces the range of mileage. What kind of effect does that have, or why is it affected?
I mean, heat on any battery isn't very good, just because the batteries themselves can overheat and just malfunction and possibly blow up. But yeah.
So think about it this way. So what makes capacitors fast? Or what makes batteries slower?
They're slower because they take longer to charge.
And
so
how are they getting charged?
So we talked about lithium-ion batteries, and so in that sense, the lithium ions are moving around, and in a battery, they're actually separating the layers of the substance they're in, so that's actually a really slow movement, and the lithium has to move through a substance, and that's way slower than it is in something like a capacitor, where it's actually just moving way faster.
Yeah, so batteries go through a chemical reaction, right? Whereas capacitors, you're just doing it on the surface itself.
Mm-hmm.
Right. So what role might temperature have in a chemical reaction?
it would speed it up versus slowing it down.
Yeah, so if you cool something down, would it speed up the reaction or would it slow down the reaction?
Slow it down.
Exactly. Yes. So that's why people put things in freezers, batteries in freezers, because it slows down the chemical reaction. But for capacitors, it's not going to matter at all. For batteries, it will.
Any last questions? And if not, let's thank our speakers. And then where's our other supercapacitor team? Up back there. Did you guys have anything that you wanted to add to what they said? You can just grab the mic from Andrew if there's anything you wanted to add. Or did they get it all pretty right? You got it all pretty right? Awesome. Nice drawing. Okay. Next group. So this is Bryce, Anish, and Matthew.
Shows who the author is. All right. So what's going on, guys? My name's Bryce, and I'm here for the Nanoscience program. This is Anish, and this is Matt. We're very close, and today we are presenting to you our what we've learned here, pretty much. The specific topic today is plasmonics, specifically plasmonic resonance. And in order to understand that, you need to understand a little bit about nanoparticles. We've already had a group go up and talk about plasmonics, so this might just seem like a blatant ripoff of Nora and Becca and them, but I swear we came up with all this on our own. So nanoparticles, the ones that we've created at least, we made in about 2 hours. So they're a pretty simple thing to make. The word like nano and particles, you think of like some super sciencey thing, but they've been around ever since like the ancient Romans. They had that cup that changed colors. Notre Dame is old. The rose window, that. Is it not old? It's an old church, and the window there, the light, the change of color is all due to nanoparticles. So despite the fact that people haven't known about how nanoparticles work, how to create them and whatnot, hasn't changed the fact that they've been useful and they're going to continue being useful for all time. So how we created nanoparticles was we used a metal. And for nanoparticles, you want to use a Nobel metal. I don't know if people here are familiar with the periodic table, but Nobel metals are more stable than other metals. And so like gold, silver, copper, that's what you want to use for creating nanoparticles. And in addition to that, you need what's called a capping agent and a reducing agent. In our experiment, the citrate was both of those things. It was a better reducing agent than it was a capping agent. And so to explain capping in basic terms, because I don't understand it in complicated terms, it basically keeps all the nanoparticles from grouping up and aggregating. That's a word that was thrown around a lot. And reducing agents, what they do is they give away electrons, which is kind of counterintuitive to the name, but they give away electrons. And the only thing else that we had to do in the reaction was stir it and heat it up. And heating it up was just to speed up the reaction, as was previously talked about. And so it's a pretty simple process to create. The nanoparticles that we made were called nanostars. And this is something that Anish and Matt will both talk about as well. But the reason why nanostars are interesting is because they have a higher surface area to volume ratio due to the fact that, like a star is pointy, it's got things coming out of it, so there's more surface area to that. So that makes it more unstable. So that's something interesting, and just keep that in mind as we go through the presentation.
All right, so on the surface of this analogy, it's obvious that there's an opera singer reaching an extremely high note, as you can see, and that frequency and sound being absorbed by not the smaller wine glass, not the bigger wine glass, but the one particularly in the middle. And then in the next frame, you can see it shattering because of how strong the frequency of the opera singer is. But this is meant to manifest a big concept in nanotechnology of the scattering of light and the absorption of light and the scattering of light in that order. So what's happening here is that when So when light hits a nanoparticle, for it to appear to like the eye, it has to the frequency of the light has to be the same as the frequency of the electrons that are oscillating. So that would mean that, and it particularly hits the middle glass because those electrons are oscillating at the same frequency of the light, while the bigger particle that's displayed in the bigger by the bigger glass, the electrons are oscillating really slowly because it's slower than the frequency of the light because the particle is bigger, and vice versa with the smaller one. And in the next frame, it is shown that middle glass completely shatters, it explodes, and with all those energy beams and stuff. I don't know. And so what that is intended to represent is the scattering of light. And I think that a limitation of this is the fact that a color plays a big factor into this, because the color of the light absorbed is actually complementary to the color of the light that is scattered by the nanoparticle. And yeah.
All right. Well, beyond analogies and simply making gold nanoparticles themselves, there are actually a lot of applications, especially in the biomedical field, for nanoparticles. One effect that was kind of touched on by Bryce earlier was the photothermal effect. And so in these gold nanostars, because they have this higher surface area to volume ratio, they're able to collect heat much faster than other shapes. So, for example, when targeting tumor cells, one thing you could do is attach these nanostars to the cell, and then you can use infrared light to actually heat up and destroy the cell. Additionally, if you wanted to use nanostars differently, you can directly target and deliver drugs in a more efficient manner, so that, say you have cancer, you wouldn't have to undergo chemotherapy. Additionally, you can treat allergies using nanoparticles. So by using these nanoparticles, you can target the liver, and what that would do is suppress the immune system, so that in case you eat anything you were allergic to, you would no longer have that allergic reaction. You can also have this opposite effect, where it would excite the immune system, in which case you could help fight off any illnesses. Outside of the biomedical field, it was mentioned in the first presentation, but with the rose window, you can make stained glass by choosing differently shaped nanoparticles, which in turn produce different colors. Thank you.
Yeah, thanks for listening.
Questions?
Nice.
Taught them everything. They don't have any questions.
Yeah. Right. So you mentioned at the end targeting the nanoparticles, so getting them to go to the tumor cell or to the liver for allergies. How exactly do you target the cell? How do you get it to go where you want it so you can heat it, or so that it can prevent the allergic reaction?
So generally, you can shape the nanoparticle very specifically, depending on the shape, size, the material, and the environment. And so what it does is it's structured so that it only attaches itself to that specific cell you're targeting.
So I'm going to add on to her question to give you guys a little bit more of a chance to answer. So the shape and the size doesn't necessarily dictate where it's going to go. In some cases it can, but more specifically, there is a thing that you can put on the nanoparticle to get it to go where you want it to go. So when you're synthesizing nanoparticles, you mentioned something that prevents it from aggregating, which is
capping agent.
The capping agent, right? So you can coat nanoparticles with things. So there's a thing that you can coat the nanoparticle with that will make it attach to or go into specific things. Do you remember the term for that?
Antibody? Oh, it's an antibody.
It's an antibody, right? So you can attach molecules, just to answer your question before, you can attach molecules so that's why it would go to the cancer cell specifically, because the cancer cells would respond to it, whereas other cells in the body do not.
So is it live or is it Memorex?
Sorry, what was that?
That was a joke. That was meant for the older crowd.
Oh, sorry. Yeah, no, I'm not in the older crowd.
Oh, you're a boomer.
I'm a boomer, yeah.
Seems like it's live singing to me, but it could be Memorex. I don't know.
I don't get it.
I'd like to think that the artist was depicting me singing because of the curly hair, but who's to say? I don't know.
That's a really high note, too.
Yeah, I mean, you know, I'm no soprano. I'm an alto, but, you know, I try. Other questions?
So you talked about the difference between stars and like regular spheres. How is the photothermal effect different in stars versus spheres?
So the nanostar has a greater surface area than the sphere. And so because it's more spread out, it can absorb heat on a greater amount of surface, and then it can heat up quicker.
Specifically, where in the star and where in the sphere would you have hotspots?
Specifically,
It would be the tails, right?
Yeah.
The tail ends of the stars, or the points, yeah.
Yeah, so the photothermal effect is much higher there, right?
Yeah, and that's like what makes it more unstable.
So like Bryce stated earlier, kind of like with increasing instability or like a greater surface area to volume ratio, you can gain heat quicker.
I guess the last question, another question if no one has asked.
I have a question. So you talked about being able to, you know, tune nanoparticles based on size and shape and get different colors as a result. There's a really big application other than medical applications that specifically utilize the fact that you can produce these colors. So do you know what that would be?
Is it Raman spectroscopy?
That's a way of being able to analyze stuff. But I mean, like, so there's a big actually consumer electronics application that uses the fact that you can generate a lot of colors with these particles by exciting them.
Would these be screens? Like television screens?
Yes.
It's like a cathode.
Mm-hmm. So can you describe maybe a little bit about how that might work? So how would you, so you would make different colors based off of what? Changing three, you can change three things, or you can
yes.
change three parameters to make
so
different colors, right?
you'd have green, red, and blue lights, right? Or
Well,
that's what they have
you can change the color that the nanoparticle is based off of changing what things?
Size,
The size, the shape,
composition.
and the
Temperature.
composition, right? So when you're using nanoparticles specifically for the color or to, and you saw this in the light microscopy lab, right, where he used these different nanoparticles basically as like staining tools to like color stuff. Do you remember what those were called?
Wait, he talked a lot about quantum dots. I don't remember.
Yep.
Oh, is that what they were called?
Yep.
Oh, no way.
Wow, okay.
So quantum dots are actually a really big application right now for television screens, right? So if you hear about like QLEDs, those are trying to use these plasmonic quantum dots for television displays. Other questions? Last questions? And yes?
Wondering more about the experiment. What colors did you observe, and were you able to extrapolate what kind of shapes you were creating?
So how we figured out, or I'll start with the color. So when you use gold, as you can note in the rose window, it creates like a red pinkish color, right? And we learned a lot about complementary colors. So say you reflect something that is purple, you get
yellow.
I was about to say that. You get yellow as the light that comes off it and the light that you actually see. In terms of how we actually know that we created the stars, how do we know that
they were unstable, and when we were heating them up, they were changing colors. If you were to stir the water, it went from like blue to like purple.
But like how would we tell that it's a star versus a sphere?
Because the spheres are more stable than the stars.
Oh,
Well, you also used a technique in the afternoon.
One thing is a spectrophotometer. And so what it does is it measures the absorbance of light and which frequencies of light are observed. And so the way it works is it shoots a beam of all these different frequencies, and it picks up the absorption at the back. And so when you see two peaks on the graph where two different types of absorptions or wavelengths are absorbed the most, you can see that there are two different colors being absorbed. And the way, when you see electrons oscillate inside the star, they're kind of going on different planes and at different speeds, where on the point of the star, they're going much quicker. And so they're going to produce wavelengths of higher frequency and a different color. And in the sphere, they're going to go much slower, so that they produce light of, like, say, red.
And then what was one last way that you saw the different shapes, or that you knew that you had the different shapes? What technique did you do to actually verify what your particles looked like?
Can I get
You stuck them in a big machine that let you observe what they were. Do you remember
electron
what?
microscope?
Mm-hmm.
Oh, okay, come on. I did use
So what's the
We did that.
resolution of an electron microscope, roughly? What is it?
Yeah. I thought you said it was an electron microscope.
No,
My bad.
Sorry, I'm asking, what is the resolution of an electron microscope?
Okay, so electron microscope. I'm not sure about like an exact, like if you're looking for like a quantitative.
Like nanometers.
A few nanometers. A few nanometers, and that's because how an electron microscope works is that it actually shoots down like an electron beam, and so like things like air, dust, and whatnot can mess that up, and so you're looking at a very
airtight.
a vacuum. You're looking at a very small area, and then as we also learned in, I forget the name of the lab, but you can basically wrap a laser in another laser and then squeeze it super tight, and theoretically you can create a viewing, I don't know, like a viewing size, I guess, of like less than 1 nanometer, but due to the fact that you can't actually create a laser that squeezes it that tight. It's theoretical, it's on paper, it's possible, but in real life, it's not practical.
Any last questions? All right. Thank you, guys.
Yeah, thank you.
Thank you.
And then would the artist behind this drawing stand up? Nicely done. Is there any concepts that you were also going for that they didn't get to talk about?
They pretty much got it. Yeah, it's just when the glass explodes at the end. I was actually going more for the. We talked a little bit about like the photothermal effect. If you do it too much, then the arms on the star break down. So like it like overheats and then doesn't work anymore. So that was kind of more what I was going for instead of scattering light. But everything else, like, they got right on the nail. So.
Nice, thank you. All right, so we've all been sitting here for a bit now, so let's give ourselves a little bit of a break. So let's take maybe a 5-minute break, and we'll come back here and start again at 3:45. So get up, stretch, use the restroom, do whatever it is you need, and we'll be back in 5 minutes. right, so as we're all sort of filtering in and getting back to our seats, if our next team could come up. So that would be Abe, Callaway, and Powell. Yeah, let's give them a round of applause.
Okay. I'm Abe. I'm Bao.
And I'm Callaway.
And we're gonna and our topic was on the first day. So, a nanometer is a unit of length in the metric system. It's equivalent to a billionth of a meter, or 10 to the negative 9 of the 10 to the negative 9th power meters. Normally the nanoscale ranges from 1 to 100 nanometers in size. Every day we use nanostructures ranging from sports to medicine and engineering. To give you an idea of its size, viruses can be as small as 20 nanometers. Light diffraction is a way that these types of nanostructures could be studied. Light diffraction is a phenomenon that occurs when light encounters some sort of obstacle or slit. In the experiment that we did, we shined a laser through a diffraction gradient of at different heights and measured the distance between the points shown. Through the diffraction, if the point could be seen, it was something called constructive interference, and if the point did not appear, it was called destructive interference. And now Pao will explain the picture. Can I get the laser?
Yeah. Okay. So in that part over there, we can see a lot of people going out of this dance party, I think. And like when they are getting out, they are dispersing. So this is what happens when light encounters a slit. So whenever it encounters a slit, depending on its wavelength, it will bend in all directions. So it will like scatter around and go in all different directions. Also, on the disco ball, we can see the reflection of the lights. So whenever the light hits the disco ball, it's not a slit, it's an object, so it reflects what the disco ball, like the nanoparticles mostly, they reflect the light, or they show different patterns that they have inside. And also, at the very bottom, we can see two guys dancing. This reflects the destructive interference and the constructive interference. In the part they are dancing together, it's a constructive interference because they are dancing at the same rhythm. And in the second part, they are doing the destructive interference because they are not dancing in the same rhythm, and the girl tripped, or the guy made her fall. And
then, despite that, there is some parts of this analogy that don't tie the scientific concepts together as well. I think one of them is the disco ball, which is, as you see here, it's kind of creating a diffraction gradient, which disco balls don't normally do to display their light. So I think this one has some type of structure, if a nanoparticle on its surface, which is creating it to make these diffraction patterns. And also, I think that this analogy could have better incorporated the constructive versus destructive criticism or interference shown at the bottom, and has somewhat display that throughout the light. Whereas, as you see at points like here, here, and here on the disco ball, they're examples of constructive interference, since the crests and troughs of the wavelengths are meeting up. So that's amplifying the effects and makes you able to see the light patterns. Whereas spots in between the two, between them where you can't see the pattern, it's having destructive interference. So that means that the crest of one light that's being diffracted is meeting the trough of another light. And that results in the wavelengths canceling each other out, and then you can't see the light in between them. So I think that brings us to questions.
All All right, so I've got a question. So you mentioned that that when it encounters an object or a slit, depending on the wavelength, it might diffract. So can you elaborate a little bit more on that? So what do you mean by depending?
Okay, so okay, I got it written down. So diffractions is the slight bending of light as it goes through a slit on an edge of an object. And also this bending is determined by the wavelength of this light. So what I'm saying is, depending on the closure, I think, of the slit, it can also bend in different certain ways, but mostly because of the wavelength, it will bend more or less. Like it will scatter more, wider, I think. So.
So right, so diffraction is occurring when light encounters an object or a slit that is
On the same on the same wavelength as the object is.
Yeah, so an object or a
similar.
slit on the same length scale as the wavelength. And what is the wavelength of light?
From 300 to 700 nanometers.
Yeah, approximately.
So any other questions?
I will sit here awkwardly until a parent asks a question. Although Andrew has one too, so we will let Andrew ask one. But I will make every round of students have a parent question. But Andrew, yeah, go ahead.
So if you look at the nanoscale, like tens of nanometers, what type of light would you need to do diffraction with?
Can you repeat that? I didn't hear it.
So if you're looking at nanoscale objects like tens of nanometers, what wavelength or what type of light would you need in order to identify diffraction patterns?
Okay, so that day we did, I think we went down and did and they explained us a way to reduce the scale of the wavelength, reduce it to half of it, but I don't know about 10 nanometers, so probably we would use I don't know how to explain it, but it's like a sensor in a microscope that goes like line by line. I don't know how to explain it.
Yeah, I think what he's trying to say is you could use waves that are at the length of the holes of the 10 nanometer, and then use some type of sensor to pick the diffraction. So whereas with diffraction with white light that we can all see, we can use our eyes or a microscope to do it. But with something like that, we would use smaller wavelength on the electromagnetic scale, and then we could use sensors to pick up the diffraction.
Yeah, I think some of the talk you listened to was about X-ray diffraction, so you would use X-rays a lot of the time.
Or you can also
use the scanning electron microscope.
Yeah, right. So you can also use electron diffraction. So diffraction doesn't just occur with light; it occurs with any type of electromagnetic radiation, or any type of wave. Really, you can diffract with water, with all sorts of stuff. Parents. Or students. I will make one of you ask a question, and I will wait. Excellent.
Yay.
Well, you mentioned about nanomolecules like viruses or bacteria. Say virus doesn't have a cell membrane. Okay, how do you detect virus using any kind of wavelength or using imagination? How do you make any kind of, using light, the method you just described to detect virus and find its properties?
Well, I think you could use like wavelengths as the X-ray diffraction, like at the length of the virus, and you could use that to kind of figure out the properties.
When you guys were at the, remind me, when you guys were at the electron microscopy demos, either at the scanning electron or the transmission electron microscope, did they talk to you about cryo-EM, cryo-electron microscopy? or did they talk about some of the more complex structures like proteins that you can use, that you can analyze with X-rays?
I don't believe so.
Yeah.
Okay, so so just to answer a little bit more your question, since it is an interesting one. So you can do what's called protein crystallography, where you use X-ray diffraction to try to resolve really complex structures like proteins by trying to make sort of crystallized versions of those proteins. But one thing that scientists are doing now is instead of using X-ray diffraction, because that's a lot more complicated, is something called cryo-electron microscopy, where you basically like freeze the virus in glassy ice, and then you put it under an electron microscope, and you view it with a bunch of different angles, and then using software, you can sort of resolve all of those different pictures into one three-dimensional image. And so that is how you can use these types of techniques to get images of really, really small things like viruses. Any last questions? And if not, let's thank our speakers. Nicely done. Before I move on to the next one, who is the illustrator of this one? Did they get everything you were going for? Any additional concepts you want to add?
Sure. Yeah, they mostly got everything. They got the constructive, destructive interference, the diffraction of the people going through the opening door in the slit. One thing I was trying to go for was we used an optical grating that day in our lab experiment. So that was kind of the lights shining on the disco, and those dots were the disco, like the colored patterns, which we weren't allowed to use color, so that was I was trying to portray that, but they were, in class we used the grating and we shined a laser through it and they split in a certain pattern. So that I try to arrange the dots in a pattern so it's easier to see that in the middle group of colored dots where it goes 2, 3, 2, 3, 2 from top down. So that was kind of the pattern I was trying to portray, but that was the only thing. They did a really good job though. So.
Thank you. Nicely done. Okay, next group. So Jaden, Aaron, Kyle.
Hey, hello, I'm Jaden. To my left is Aaron, and to my right is Kyle. And today we'll be talking about biotoxicity and how we use silver nanoparticles to basically kill microorganisms. Okay, so I first wanted to start with how we made silver nanoparticles in our lab. So we used silver nitrate, and then we reduced it, which was basically means added electrons to silver nitrate using sodium citrate, which I think another group talked about. And then we put that on a hot plate and used excess sodium citrate to prevent the particles from combining together to create something larger than a nanoparticle, because nanoparticles have the right amount of surface area and like structure so that we can easily kill bacteria. And then after that, we basically used heat to make sure the nanoparticle was the right size. Okay, so a few applications of silver nanoparticles would be anything that basically kills microorganisms, such as, I think they are used in bandages and also like mouthwash. So yeah, it's pretty interesting.
So in this experiment, we tested the effectiveness of 4 different ways of, or at least attempts to kill cells. So we used yeast cells, and pretty much we determined whether or not they were killed by using a manometer to measure how much carbon dioxide was being produced. So obviously if there are cells due to cellular respiration, more carbon dioxide will be produced, but if whatever we put in killed the cells, then less carbon dioxide would be produced. So for the analogy, the hearts represent the nanoparticles. So the white heart is the silver nanoparticles, and the darker hearts are the gold nanoparticles. So pretty much the first part of the analogy is how they enter the ride. So if you'll see, both of them have to have like free hugs to get onto the ride. So I think this is demonstrating how nanoparticles enter through endocytosis, which is pretty much the membrane allows them to come in and then sort of hugs them and brings them into the cell. So that's how the nanoparticles get in, because they have no charge. But the ions, which are the triangles, because they do have a charge, they can't get in through endocytosis, so they have to enter through ion channels. So as you can see with the triangles, there's a little tunnel. So to get on the ride, they have to enter through the ion channels. And then the bulk silver, which is the circle with triangles inside. So as talked about by the earlier group, the bulk silver can't fit in, so the ions have to come off of the bulk silver to get in, which is much slower. So as you can see, I think the speech bubble says like must be this small to ride. So pretty much they have to separate. The triangles have to come off of the bulk to go on the ride. And as you can see, there's only 2 triangles on the ride, while all the other rides are filled up because it's such a slow process. So after the entry, the next part of the analogy is the damage that they all do to the cell. So as you can see, the silver nanoparticles on the left, which are the white hearts, there's a speech bubble that says this ride is broken. So pretty much silver nanoparticles do the most damage, and therefore, as you can see, they pretty much the ride fails, which pretty much means the cell would have died in the experiment, and we saw that as there was less carbon dioxide being produced. But as you can see on the right side, the gold nanoparticles, it still says this ride is so fast. So actually, since gold, it doesn't have the toxicity of silver in terms of killing the cells, so it wouldn't be effective if you insert it into the yeast cells to kill them. So that ride is still fully functional. And as you can see, the one with the bulk silver is also fully functional because since the silver ions enter so slowly, it doesn't have enough of a harmful effect on the cells. And then just the pure silver ions, the kind of in between where they had a negative effect on the cells as the carbon dioxide went down, but not as much as the nanoparticles. So it just says this ride is slow. So it's kind of like not completely killing them, but it's not killing all of them, but killing a large portion of them.
So scientific analogies have limitations, and it's extremely difficult to encompass many concepts in one analogy. And as a result, our analogy doesn't quite encompass every concept we learned in the process. So one thing that the drawing leaves out is the process in which our silver products actually kill the bacteria or the target cell. So after each silver product ultimately sheds off silver cations, the cations then oxidize the oxygen atoms present in the cell, and that ionizes and makes the oxygens extremely reactive. And these new reactive oxygens then bind on to the nonpolar hydrophobic components of the cell's membranes, which includes the mitochondria membrane and the actual cell membrane. And it turns these nonpolar components polar and hydrophilic. And without any hydrophobic components to the cell membranes, the cell membrane is unable to conserve its phospholipid bilayer structure, and ultimately it just collapses into itself. And this obviously kills the cell, and yeah, that's basically how it kills bacteria or unwanted cells.
Any questions?
Okay, I'll start. I have a couple. So first, you mentioned how the silver is toxic to the yeast and the gold is not. So they're both nanoparticles. So why is one toxic and one not toxic? What's the difference?
So silver has a charge of +1, whereas gold has a charge of +3, and so silver is more reactive or more easily oxidizes the oxygen than the gold.
Right, so if you see like silver, just like in general, like if you have silver plates or silver spoons or silver jewelry or whatever it is, what happens to silver over time normally?
It reacts.
It reacts to?
everything surrounding it because it's so reactive, because it's +1.
It oxidizes, right? It
Yeah.
tarnishes. So gold, does it do the same thing?
No.
Right. So is it reactive to gold?
No.
Not really, right? Good. Another question I had is, so these ones, I do see that they are trying to capture differences in size with the triangles and the circles having more triangles and the hearts having less triangles. What is the actual size ratios of the 3 types of silver?
So the silver ions are actually the smallest, and then the nanoparticles are actually bigger than the silver ions. But because they have no charge, they can enter through endocytosis, while the silver ions can't. And then the bulk silver is the biggest.
Right. So in terms of like the actual size, though, like how big is an ion? How big is the nanoparticle? And then roughly, how big is the bulk?
Well, an ion would probably be like picometers in size, probably, right?
It's it's like fractions of a nanometer.
Yeah, and well, obviously the nanoparticles are around in the nanometer range. So like probably maybe 5 to 20 nanometers, and then bulk is like probably micrometers.
Yeah. So really, really big differences in size. Oh, so many questions now. Okay, cool. Here, let's start. Go ahead.
This question goes back to what was brought up earlier, where someone consumed so much silver that he turned blue. And it seems to be not hurting him, but then my thought was, will he stay blue? Or will the body expel the silver?
We didn't, I'm not 100% sure about this, but I assume that the body would continue to make more and more cells, and therefore it wouldn't. It would eventually go back, but I can't.
And I also think some materials can't be dispelled from the body really easily, and I'm pretty sure silver is one of them.
Yeah.
So time will tell, but maybe he'll stay blue the rest of his life.
As the silver oxidizes, right? Does the silver ever lose its potency or the ability to kill the yeast through time? And if it oxidizes, can you polish it again or get it straight back?
I think when the silver oxidizes the oxygen, it just kind of loses or it gains the electron. And I think it just, I don't think it can.
I think in theory it is possible to reverse it, but in practice, I'm not sure if it would be possible.
And then was there one more question? Yes?
Can you explain how you quantified the damage done in each sample?
So we pretty much had the manometer capped onto the combination of yeast, sugar, and water with a stopper. And pretty much if the yeast was creating carbon dioxide, the manometer, the water would move. So you could see that there's more gas, and therefore we measured how much the water moved up, and that meant that there's more carbon dioxide being produced, while for certain ones like the nanoparticles, the water would actually move down because it was using oxygen for cellular respiration, but then eventually the yeast cells were dying, so it didn't complete cellular respiration and not enough carbon dioxide was produced, so the water level would go down. So we just measured how much it went up or down.
Any last questions? Oh. Wait, sorry, Elaine's gonna, or you're gonna get there you go.
So when you synthesize the nanoparticles, you created 10 nanometer nanoparticles. How did you synthesize them and know how to grow them to a specific size?
I think eventually just the sodium citrate decomposed completely, so they wouldn't expand more, but yeah. I'm not sure, but maybe some of my teammates can respond.
So here, let me help you guys out. So you guys learned from plasmonics that what happens if you're observing a color change?
Oh, the particle might be getting bigger, or like might have like more arms, more surface area.
So then you're using what to determine what then when you were synthesizing your silver?
Oh, we were using light to determine, or the color.
The color, yeah.
To determine. Oh, okay.
So when it turned more yellow, that's when we took it out. Yeah.
Any last questions? All right, thank you guys.
Thank you.
And then can our artist behind this drawing please stand up? Yeah, we'll give her a round of applause. Very nice. Any additional concepts that you were going for that weren't mentioned?
I think they covered everything pretty well. I especially like how they noticed the hugs representing endocytosis, because I know a lot of people didn't get that when I showed it to them. And also the ions in the nanoparticles, because that myself I wasn't sure of when I was drawing the picture, but some of the instructors helped me. So yeah, it was really cool how they got everything.
All right, thank you. Okay. Next group is Wesley, Ashish, and Jeffrey.
Good evening, guys. I'm Jeffrey.
I'm Wesley.
And I'm Ashish. And we're a couple of high school students at the Nanoscience lab, and we're hoping to shed some light on photolithography. So photolithography, if you take just lithography and you look at the Greek roots, it literally means banging things together with rocks, which is kind of counterintuitive. But actually, it's kind of like engraving something from another thing onto another object. So if you take photolithography, that means photolithography is on a much tinier scale, hence nanotechnology. To visualize this, you can think about it as, I guess, a stamp. And when you stamp it into a wax mold, it kind of gives the seal of it. So photolithography is mainly used in microfabrication to pattern parts of a film. And in this case, it's going to be on a light-sensitive material called a light-sensitive polymer called photoresist. So once you have the light-sensitive polymer, you use chemical treatments to build on the initial foundation to form 3D structures by either etching into the original material or depositing more material to build like a 3D structure or model. And at one of our labs at CNSI, we experimented by creating a couple of very small wires using photolithography techniques. And here we see the inherent usefulness of photolithography because it's in everywhere. It's in your phones, it's in your computer screens, and a good way, and to think about it this way, Richard Feynman, one of the forefathers of nanoscience, once famously stated, "There's plenty of room at the bottom," and indeed, there was. Photolithography is what makes technology, like your phones, again, possible. Thanks to photolithography, thousands or even millions of tiny resistors, capacitors, or transistors can be stored onto a very tiny chip called a microchip, something smaller than a dime, which is pretty interesting to think about. It saves space and allows for immense complexity on such a tiny scale. And yeah, so on to Ashish.
All right, yeah, so it's the last day.
Sorry, they're brothers.
No,
They're
brothers.
brothers.
So along with that, that was like the main aspect of the experiment. But I guess the side aspect would kind of be to measure the resistance and the resistivity of the materials that we're actually creating. So just to define two terms before I actually delve and break down into the actual analogy. So resistivity is the actual inherent conductivity of how well a material conducts, like electricity. And resistance is the energy lost in the form of heat. And it also takes into account both the geometry, so the size and shape of the wire, and also the resistivity. So as you can see in the picture, there's these people that are trying to cross a river, and they can do this in two methods. So the first is by crossing crossing a ladder. And the next method is by crossing the bridge, which is actually like shaded in. So basically you can break down how resistive or resistance, how much resistivity or resistance something has by the actual size and shape like I mentioned earlier. So the first thing we're going to compare are the thin ladder and the thin bridge. So if we look at the picture, there's more people on the other side of the thin bridge, showing that it's a better conductor. And the actual reason that is because, it has to do with the actual resistivity of the material, so it's just naturally a better conductor. And that's the reason why more heat or more energy is conserved in the actual process when electrons go through the wire. And the next thing we can compare is between the thin long wire and the thin short wire, the bridge, which is on the very edge of the right side of the paper. And basically what happens is that in the long bridge, there's more distance for the electron to travel. So there's a higher chance of interference going on. So that's why on the top of the bridge, there's only one person, where if we look at the shorter bridge, there's actually 3 people. So that kind of shows that the longer bridge has a lower resistance. So that means it loses more heat. And the last thing we can actually compare is the width of the bridges. So we can compare the long thin bridge to the long wide bridge. And if we once again look at the picture, we can see that there's 4 people on the wide bridge compared with 1 person on the thin long bridge. And what's actually going on between these 2 bridges is that the wider bridge has a lower resistance, which means that it's actually losing less heat and conserving heat better than the thin bridge. So yeah, basically it's losing less heat than the other bridge.
All right, so the ideas of resistance and resistivity can be applied to photolithography. So specifically, a photolithography is a fancy word for patterning or transferring something from one surface to another. And this is good because it can save space, heat, and energy. And there are different types of photolithography, such as electron beam lithography, mechanolithography, scanning probe lithography, and photolithography. And among those, we studied photolithography. And photolithography is basically made up of 2 things, UV and laser. So then the copper wire experiment that we did is the UV one. And there are 5 different steps for the patterning. The first step is coating, which is done already for us, which was the copper film being covered with a light reactive polymer called photoresist, as Jeffrey said. The second step was masking, which made sure that the pattern was going to be generated. The third step was exposing, which we did by exposing the sample to UV light for 12 minutes. And then the next step was developing, which was putting the sample into a base to make sure that the only exposed portions are removed. And the last step was etching, which was the actual removal of the copper on the sample, or like the plate. And we also learned that there were 2 types of resist, like the other groups already said it. It was positive and negative. Positive resist being that after exposure to sunlight, it would be less soluble. The bonds would be stronger, weaker. Yes, weaker. And then negative would be the bonds would be made stronger, which we did the negative resist for our cyanotype activity in the afternoon with the blue paper and the plants. And last but not least, other applications of lithography can be used for iPhone screens, like Jeffrey said, camera sensors, and projectors. Yeah, that's it. Any questions?
I have some like basic questions. I can't read any of the words just because, you know, I'm old and I have not great eyes. What are the people saying?
I don't think we can either.
Oh,
I got it.
Yeah.
Okay. So the person in the middle,
Are they happy words or sad words?
oh, they're pretty bad. They're like, we're gonna get killed or something.
I'll help you out. It says we have to get across the river or we are going to be killed. Hurry up. That's
Yeah.
what the big speech bubble is saying. And so if the other words are just people basically like failing at getting across because they're on things that are making them fail to.
Yeah, it's meant to show like resistance. So like the more people falling off, that means that's like a representation for heat being lost.
So I guess my question is so you guys described a bunch of things that was great about long bridges versus short bridges and wide bridges versus narrow bridges that all directly maps on to resistivity.
Yeah.
I am confused about ladders versus bridges.
All right, that's the material part, the inherent resistivity of the actual material. So if you can see, for the middle bridge and the bridge on the left, one of the ladders is short and one of them is longer. But the longer one is there's no one going across, which means that distance has. Oh yes, thank you. How do you turn it on?
Good question.
It's a test.
It's like.
Oh, I got it. Okay.
Oh,
Sorry,
it's a
my
good
bad.
laser pointer.
Yeah, it's a great one. So, so the ladder is made of a different material than the actual bridge, which is wide. It's pretty strong. It's sturdy looking, you know. So people get across, but the people who go across the really long, narrow ladder, they just fall in the river and die. So, that's not good. But
Well, they don't
what
die,
I'm
they
trying to
fall
say
in.
is these two are very different materials, so they have different resistivity processes. And also, actually, in a speech bubble made by, I think this guy. Am I pointing at it? Sorry. Oh, it's kind of dying. But there's a person to your right. There's a speech bubble. It says, the ladder is so slippery. So that shows one of the other materials.
Okay, so that is the other way to convey that it is a different intrinsic kind of resistivity. It has a different baseline resistance, and then you can also modify it by width and length.
Yeah.
Okay, other questions? Just because
Anish,
it's
no?
the second time that you've seen this topic, or the third,
I think
doesn't mean you don't have more questions.
So we talked about ways of diffraction, right? X-ray diffraction and electron diffraction. What do you think is one reason you would want to use electron beam lithography versus photolithography?
Well, I mean, it has like a smaller wavelength, so it's more precise. So like if you're going down to like a nanoscale, it's better to use electrons.
Yeah. What is the limit of the sort of the size of things you can make with light?
Well, I mean, if we're talking about like practical terms, it's like 300 nanometers, so like visible light. Well, I mean, actually, we can go down smaller distances, but.
But you just sort of in order of magnitude. I'm not worried about precise things. Maybe I should ask it differently. What determines how small you can go with any particular kind of light?
Like the wavelength, so like how long it is, how long the wave is.
And so for light like the UV light, what is that? What kind of size is that?
I'm going to defer to Wesley. Or my other teammates.
You already said it close enough for me.
You can ask my friend Siri.
Order of magnitude
Thank you.
answer.
Well, I mean, I guess UV light has, I guess, a smaller wavelength. So it's kind of like the laser technology they use for lithography. I think that was one of the things that we mentioned, if
Well, you gave a wavelength before. What wavelength did you give?
Like 300 nanometers.
Yeah.
Yeah.
So that's the order of magnitude. Few hundred nanometers
Yeah.
with visible light.
Mhm.
Can actually get down to like wavelength
Yeah,
over
smaller.
2. So a little less than the wavelength, but that order of magnitude. So if
Yeah.
you want 10 nanometers, you are not going to get there with visible
Yeah.
light.
Yeah.
That's the concept.
So a slightly different topic. So you talked about using the mask to create the pattern that you were essentially going to etch on. How do you get the mask made to that kind of precision at that time so that you can do the transferring? I understand once you have the mask how you get it onto the material, but somehow you have to make the mask. Did you learn anything about that?
Well, I mean, like we didn't learn about like the specific like manufacturing process behind constructing the masks, but I'm sure it has to do with like something like somebody else made in a lab, but we didn't like specifically learn about it.
Well, like what kind of mask did you guys use? Low tech.
I think we did the copper wire.
No, your mask.
That was the
mask.
mask. Oh.
Like, are you talking about like the material composition of the mask, or
What did your mask look like?
like it was black?
And what? Partly black?
Yeah, and it actually like blocked out light. So if that's
No,
what
it was
you're
like a
asking.
peel off, then we
Yeah.
stuck it on to the thing.
Yeah, I'm not actually sure about.
Just very generally, not specific.
Like a plastic, probably.
Plastic?
Like some
It's like a
polymer.
polymer.
Their mask was just printed in a laser printer, black on clear plastic.
Yeah.
Okay, so their mask was not high tech. It was black printed on transparency. A very black, I might add, especially black, but it was just
a clear
black
piece
printed on
of
transparency.
paper or
But that's
plastic,
because
yeah.
your structures were just a little bit, they were in the micron scale, not in the nanoscale.
Yeah.
So I would say if maybe the question is, if you wanted to make a mask that was a whole lot smaller, that was in the nanoscale, how in the world would you do that?
I mean, I'm guessing that you'd use like some kind of, like you'd use nanotechnology to actually like manufacture it. So you'd use like an electron, like you'd use like electrons to actually like shine a beam of electrons and actually like make sure that the mask is like a small enough distance to actually cover like a small amount of like copper or whatever you're using.
Yeah, that's actually right. Use an e-beam writer. Do you actually machine it with electrons in an e-beam writer to? And they're super, 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 super expensive. And we don't use those. But then you get to use them a lot of times, which is the whole goal. Okay, other questions? Okay, I'm going to ask a super quick one. You said at the beginning that this stuff is called lithography, and that lithography has to do with rocks, and you said it has to do with smashing rocks together, but it does not have anything to do with smashing rocks together, but the name lithography does come from rocks. So where's the rock part of lithography?
Oh, it's actually
Like
graphite, or it's lithos, which is actually stone.
Stone,
Yeah.
yes, but and it is indeed based on stone. What aspect of that?
Well, you're kind of etching into the stone.
Yeah. The old way that you made copies of pictures is you took stone and you chipped a pattern into it, and then you inked it, and then you took the inked stone and you
like
pressed
a
it down on paper. So you transferred the pattern from etched stone, you put paint on it, and then you inked it down. And that there's still a very classic way of making art is to make etched stone things that you put ink on. And that's where the litho comes from.
So it's like kind of like a stamp, right?
It's a stone stamp. And you can make different pieces that you ink with different colors, and then you can stamp them down and make different colors together. And so many, in the not so long ago, there was a bunch of art that is made by, you make a lithograph and you make the stone things and you transfer it, and then you destroy the stone things so that there's a finite set of copies that could be made. Until recently, that's how great art, multiple copies, was always made. So, okay, good job.
All right, so while the next group is coming up, which is Lucas, Michael, and Kaushal, can the artist behind this one please stand up? Wait, so you guys are the next group coming down, but then... Yeah, I'm the
artist
you're the
as
artist
well.
Oh, excellent. Anything to add?
Basically, they got it 100%. I just add that as well as the ladder being slippery, someone also mentions that they fell through a hole in the ladder. I know it's impossible to see. Sorry about that, but so that's just adding to the inherent resistivity of the ladder versus the wooden bridge.
Cool. All right, thank you.
Hi everyone, my name is Lucas.
I'm Michael.
And I'm Kaushal. And we're going to be talking about supercapacitors. So energy demand is at an all-time high right now. So we're creating a lot of energy and we're using a lot of energy. Was that from you? Okay. So we need a way, and since like for solar panels, most of that energy is generated in the middle of the day, but we actually use most of our energy at the end of the day. So we needed a way to store the energy because we can't use it right away. And there's two ways to store energy. One way is with batteries, and one way is with capacitors. And so a battery stores a lot of energy, but it can't emit the energy very fast. And a capacitor is the opposite. It can't store a lot of energy, but it can output the energy really fast. And a supercapacitor is kind of a mix of the two. It can output a lot of energy pretty fast, and it can store more energy. So this has a lot of uses. Like the group before us talked about, electric cars can use it to accelerate really fast, like Teslas. And so the cars can charge fast, like buses can charge at each stop they make. And like at ports, the big loads that they carry, when they're coming down from the cranes, you can also use capacitors to collect that energy and store it as well. You can make a capacitor, a supercapacitor, by using nanoparticles because they have more surface area, which allows them to store more energy. And we're going to now talk about the experiment we did and the analogy.
So starting with the analogy, so when you make supercapacitors, which are a more recent invention than capacitors, so you kind of start out with a capacitor, which is kind of two plates far apart. One is positive, one is negative, and that's going to create energy for you. Oh, sorry. Should I repeat that? Did anyone hear that? Okay, so you have two plates in a capacitor, one which is positive and one which is negative, and that's how you're going to get your energy. So that's what you start with for a supercapacitor. And then what you do is you put ions in between them, some positive and some negative, and then basically those are going to get attracted to the two plates. And so say you have the positive plate, all the negative ions are going to get attracted to that, as we kind of see, and then you're going to get basically a negative plate next to the positive plate. And you're just going to put kind of a small barrier to prevent them from touching, but they're going to be incredibly close to each other, whereas a capacitor is like maybe a couple micrometers apart. The supercapacitor is going to be like on the length of just atoms apart. So then this is for us. So as you can see in the picture, the supercapacitor is going to have more energy as represented by the love meter. So which is kind of just total energy, whereas a capacitor kind of on the left, since it's not going to be able to store very much energy, so that's kind of represented by the love meter, and then as you get closer together, that's able to store more energy. And then also, so capacitors, you can also think of it in the sense that the people on the right are probably in more of a long-term relationship, which is why this is able to store energy over the long term versus people who are just kind of casual, So that could be another way to look at it. So then getting back to our experiment, we actually were able to make our own supercapacitor. And we used activated carbon in our supercapacitor. So the two plates are going to be made out of electrodes, and this is the carbon, and this carbon is on the nanometer scale. So it has an incredibly high surface area to volume ratio, because things that are really small, they have a lot more on the outside and not as much on the inside. So you're going to get much higher surface area. For a small capacitor, you could still have like a football field size in terms of surface area, because of how small all the particles are. And so when you have this high surface area, that's going to be able to create, when they're super close, you get that much larger electric field, and the much larger surface area is going to create much more energy. So now there are limits to this analogy, obviously. So to explain that.
Okay, so one thing that this analogy doesn't address is the difference between power density and energy density. So as you can see, a supercapacitor, they get very close, so they're capable of storing a lot of energy, and they can do it rather quickly. This is a little different from a battery. A battery is able to store a lot more energy than a supercapacitor or a capacitor could, but the problem with a battery is that it can only discharge that energy very slowly. And so that's why you have batteries that charge in about 3 to 5 hours and take about 3 to 5 hours to discharge. Supercapacitors can deliver a lot of energy very fast, and they can store more energy than a conventional capacitor could. So in terms of energy density, a battery is the highest, followed by a supercapacitor, followed by a capacitor. And then in terms of power density, it's a capacitor is the highest, and then you have a supercapacitor, and then you have a battery. And as Michael mentioned, as you increase the area, there's just more space, especially through nanoporous materials. There's just more space for electrons and charges to gather, so that increases the strength of your electric field, which increases the strength, which increases the amount of energy that you can store. So as Luke was mentioning at the start of the presentation, one of the applications for this is cranes. So if you go to the docks, they have cranes that unload shipping containers from large vessels, and those cranes need to use a lot of energy really quickly because they have to basically lift very heavy containers up and down in very fast. And so currently one of the big problems is it takes a lot of diesel fuel to actually accelerate the crane up and bring it to such a high position, but then when you actually are bringing the load down, you obviously can't really, you can't recycle that energy with the technology that's currently available. So that's why if you use a supercapacitor on a crane, you could be able to charge that supercapacitor while you bring the crane down, and then you can use that stored energy for the next lift. Lucas also mentioned applications in electric cars. I think the previous group also mentioned this. If you have a Tesla, they have supercapacitors which enable that instant acceleration, because those supercapacitors can dump large amounts of energy into the electric motor very fast. And then buses, that's also another example that was given. So a bus doesn't need to store that much energy for that long a period of time. So as it goes from stop to stop, it can recharge itself. And then finally, for energy demand, supercapacitors can enable us to store larger amounts of energy and be able to, discharge that a little bit faster when you have, say, solar panels that are generating electricity at 12 p.m. when you want to use it at 5 p.m. once you get home from the house, to the house. And so with that, thank you. And any questions?
So you guys, and I think also the previous group mentioned cars as a potential market for these technologies. So if you think about the Ragone plot, right, the power density versus energy density, and you kind of outlined where batteries, capacitors, and supercapacitors lie on that, where's a combustion engine in comparison to those technologies, and how close or not close are supercapacitors to reaching what a combustion engine can actually do right now?
So on the Ragone plot, an internal combustion engine is actually at the top right-hand side, which means it has very high energy density and very high power density. and supercapacitors are a little bit more towards the middle and probably the lower end vertically. So they're not quite close, that close to combustion engines, but they definitely are closer than capacitors or batteries taken alone.
You can't beat chemical fuel, unfortunately, but we have to.
So, assuming comparable energy and power density of these three technologies, how do they compare in terms of size and weight and cost?
So from what I understand, batteries may be the most expensive to manufacture because they require the most complex materials because there's actually a chemical reaction that's taking place inside. Also, as was mentioned in the earlier presentation, if you have a battery, you need to be able to ventilate it properly so that temperature changes don't affect it, and you don't need that if you have a supercapacitor or a capacitor. As opposed to pricing, from what I understand, you need more material to build a supercapacitor, so it would be more expensive than a capacitor.
Yeah, so I think about this a little different. So the question is, for a given amount of energy stored, which one do you think would be the lowest cost?
Capacitors would be the most expensive, and batteries would be the least expensive for a given amount of energy stored.
Yeah, that's the issue.
Batteries store so much more energy.
Batteries store way more.
Yeah.
So it may be cheap to make a supercapacitor, a capacitor, but they don't store much. And the materials are actually, they all have to be cheap because everybody wants cheap storage. So if you have an idea for an expensive battery, you can have your idea all by yourself because nobody is interested. Okay, another question? One more parent question? Okay, so I have a question. So you described this picture as a continuum from a capacitor to a supercapacitor. But can I ask you to look at this picture and consider also describing it as a continuum from a capacitor to a battery? And then comment on how it might map onto that continuum.
So I mean, if love was energy, then the rightmost relationship would be a battery because it stores the most, it has the most love in it. And then the leftmost would be a capacitor because it stores the least amount of love.
Yeah, so I think kind of we assumed that the rightmost one was a supercapacitor since they're so close together, which is kind of what makes a supercapacitor, two plates. Which
No, okay, but what you said was good, so just keep going with this for a minute. So you can map distance with what you said. There is a way that you can also map distance to capacitor, supercapacitor, battery. And what would it be the distance between?
The electrodes on a given.
I guess in a lithium-ion battery, you've still got lithium atoms traveling in between two sides. So would those be even closer than in a supercapacitor?
They would be even closer. They would basically be atomically touching. You'd end up with the positive and the negative thing atomically right beside each other. Whereas in a supercapacitor, one's in the solution and the other's on the surface. So they're pretty close, but they're not an atom distance away. There may be, so you're like maybe 1 angstrom, 2 angstroms away in a battery, and probably more like 1 to 10 nanometers away in a supercapacitor. So I don't know what the artist described, but that may be a different way to map it. But it's all the same concepts that you already showed. It's just pushing it's the same ideas, it's just pushing the continuum a little farther. Okay, all right, so we should thank these guys and ask the artist to stand up.
All right, so while the next team is heading up, did you guys want to add anything to their explanation?
Yeah, they touched on pretty much everything. One thing that we did add in that I'm not quite sure if they touched on or not, but was also surface area and how much that affected the love. So when they're hugging, there's a lot more surface area, and surface area meant more storage. So versus a high 5, which was less surface area.
But so how did you imagine it mapping on?
It can be, we kind of imagined it as like how effective it was almost. So versus length and then taking into account as well as surface area.
Cool. Thank you. All right, so last but not least, can our last 3 presenters come on up?
So, hi everyone, we're last group, so bear with us. So, I'm Evan.
I'm JD.
I'm Ryan.
Oh,
sorry.
It is possible to get too close.
Yeah, so today we'll be talking about how to make nanoparticles, specifically gold nanoparticles. So, as you all know by now, nanoparticles are used in like a lot of stuff from cancer treatment, electronics, and like stained glass, and a whole bunch of other stuff. So in our experiment, we made gold nanoparticles by like getting gold in solution, which like they're in ions. Then you add like a reducing agent. So you add electrons to them to neutralize the atoms. So then after that, you heat up the solution so that the gold atoms will stick together to form like a nanoparticle. And once it changes color, then you like add the capping agent, which is citrate, to like stop them from getting too large. So on to the analogy.
Okay, so I'm going to start analogy from the bottom right. It's like they are saying, remember old jewelry jacket, and what's that? Other sharp object must be removed to enter the play area. So it's like saying you need to be reduced first because they have the charge, the same positive charge, so like it plays a magnet, both north side together, they'll repulse each other. So we need to take out the charge, they are neutral, so they can come together to form a nanoparticle, and that is the top right corner doing. So they are reducing them, take out the positive charge jacket, and then the middle part is the forming of the nanoparticle. So the hamster ball is the capping agent. They prevent them to come together, and if they don't have the hamster ball, they will come together like these 2 guys. And the bottom left is the next step we are going to do, is the forming the nano star. And on the very top right corner, the sponsored by California Orange means that both the citrate act as both reducing agent and the capping agent. Yeah.
This analogy really describes really well and in depth the process of making what we called the seeds, which were the baseline gold nanoparticles that we made. But also, in addition to doing that on the same day of this lab, we also, what we did is we made 3 different kinds of nanoparticles of different size and shape to examine the effects of light on these nanoparticles. So besides these gold nanoparticles, as you can see by the +3 charge, we also made nanostars, and we also made slightly larger gold nanoparticles, and each of these interacted differently with light. And this was all in the scope of one lab. And that has to do a lot with plasmonics, which a lot of groups already went over. So essentially, light is an electromagnetic wave. These nanoparticles were all made of metal, which have like a sea of unbound electrons that can oscillate if exposed to an electromagnetic wave. Essentially, different nanostructures and nanoparticles are on different size scales, and so is light. And so the different sized and shaped nanoparticles will the electron field will oscillate in sync with the light waves, so that particle will absorb that type of light as opposed to all the other types of light. So the other type, you see more of the complementary type of light when that color is absorbed, so it gives off, you see a different color. So that's basically what happened with the gold nanoparticles. We saw red because green light was absorbed. But then later we also made larger gold nanoparticles so that those nanoparticles were, this was like kind of freaky actually. It was these nanoparticles were big enough that were big enough that they had a higher % chance of scattering light as opposed to just having light transform through it. But they were still small enough that they only absorbed green light. So we were able to see if you shined a light directly at the solution, it scattered light back at you, and you saw green because red was absorbed, or it was actually brown because there was red still. And then if you look on the other side where the light was, then you saw red because it was transformed through the solution. And so with the nanostars, we saw blue because there were the tiny arms of the stars were a lot smaller, so they absorbed another kind of light that, and in some cases, with the arms were shorter, so that meant that there was more of just the sphere base size. It was kind of a purple color that was in between blue and red. Yeah. So nanoparticles are pretty neat, and they interact with light in cool ways, and this analogy shows how you make them. Thank you very much.
Okay, we got to end our questions on a strong note.
Pressure. Okay. So a lot of people so far have mentioned citrate as a reducing and capping agent, which it is. But was citrate always used as a capping agent in every experiment you did?
No, citrate was not always used as a capping agent, mostly because citrate is not the best capping agent. So what we did in another part of this lab actually was to use hand soap as a capping agent instead. And then so we used hand soap to create another layer of capping agent around them. And then we took that solution and the citrate capped solution, and we exposed both of them to salt. And just the presence of the ions that were dissolved from salt actually completely it ruined the citrate coated solution. So those gold atoms aggregated, and it wasn't red anymore because they got too big for the light. But on the soap coated nanoparticles, the salt didn't have any effect, and we still kept the red color.
Hey, parents, this is your last chance. Your last opportunity.
Here's the billion-dollar question. You mentioned about its potential application for cancer drugs. Okay, how can you make a nanomolecule potentially to be a cancer drug that target cancer cells in the body? I'm not looking for an answer because it's $1 billion, but what do you think? What do you think? All the experiments, everything's excellent, all the things you've learned in 1 week, but how can you use that to apply to real life and medicine?
So another group kind of talked about it. It's called the photothermal effect. We'll basically use gold nanoparticles. You cap them with antibodies that are specific to cancer cells, and I guess do you inject them? I don't know. We just insert into the body, and then you shine infrared light. So it's basically red light on your arm or wherever it is. So basically the light will pass through and excite the gold nanoparticles, and the heat will kill the cancer cells.
Yeah, and I'm pretty sure they actually are already doing some kinds of like experiments with this practically in like rats. So like they'll embed a chip underneath the skin of the rat, like in the bloodstream or something, and then like they'll shine a laser on it, or that may have been for something else. But yeah, essentially like you have either a chip that you go in and then you shine a light from the outside, or another option was like taking like almost, I think it was like a loop of blood, and then there was like a little like filter that it went through with the gold nanostars on it, and then those would kill the cells if it's like cancer in the bloodstream or something like that.
There's lots of different clinical trials. The problem so far is that if you don't kill everything, but you do let them loose in the blood, then it can be worse. And so that is the challenge. It kills a lot of them, but if you don't kill all of them, it's not a good treatment yet. So I think that's why it's not a real therapeutic yet, but the method as a general idea works. You just have to make it a therapeutic.
There is also another form of using nanomaterials to treat cancer that is not based on the photothermal effect at all, but is similarly, you're using nano-sized materials for treatment. So do you remember what that might be?
Was that the silver again, or biotoxins? No, okay, yeah, I thought.
We were talking also about like lipids and how they can take different forms. So you can either have like a monolayer, you might have a sphere of them. What could you do if you had a sphere that you make that's nano-sized? What could you do with that sphere?
Oh, do you like inject like chemotherapeutic drugs in them?
Oh, yeah.
Yeah, so if the spheres are hollow, what could you also put in the mix so that what could form inside of those spheres or be inside of the spheres?
Cancer-killing drugs that would like, so you'd make these spheres that would specifically target areas in the body, so you don't have to submit your entire body to like really destructive medicine.
So I just one more question about the picture. Okay, so the hamster balls. You guys said something about this, but I think this is actually really a cool analogy to the real chemistry. So can you just say a little bit more about what the hamster balls are doing?
So the people are, it's kind of like an amusement park. The people are running around in these hamster balls, but the hamster balls are keeping them from sticking together, whereas like otherwise they have to hold hands to make sure they're safe. So basically they stick together. They're more attracted to each other, whereas they can't stick together.
So chemistry-wise, what might have been, so the people are the we're talking gold, not silver, the gold ions that are getting ready to grow on to the growing nanoparticle. In your experiment, what made the hamster balls?
The citrate made a hamster ball, but the gold ion, they don't have the citrate balls. So they have a very high surface area. So the surface energy is also high, so make it very reactive. They tend to come together.
Yeah, but that's exactly right. The capping group that caps the surface can also sort of grab single ions and change how fast the whole particle grows. That's why making nanoparticles is so hard, because everything does the same things. Okay, do we have any last questions? If not, let us thank this group. And can the artists stand up?
Anything to add?
No, they pretty much got it all right on the money, so good job. Yeah.
All right, so I know that I'm the very last thing keeping you from food and refreshments and goodbyes. So I just want to really quick say good job to all the presenters. Great job. And also thank you parents for being here and asking questions. Thank you instructors for being here asking questions. Thank you, Professor Tolbert, for being here and asking questions. And with that, thank you guys all very much. And let's all go and enjoy a little more time together with some food and some drinks.